Welcome to the calmest corner of the coding world. Find a cozy spot, kick off your shoes, and let your body sink into the comfort of your chair or bed. This tutorial is designed to flow like a soft breeze, guiding you through the basics of Objective-C with a rhythm that soothes as it teaches. Close your eyes if you like, or let the words wash over you as you follow along. Remember to like and subscribe for more relaxing coding adventures. Let's begin. Welcome to this session on Objective-C programming. Today, we will explore the fundamentals of Objective-C and how to set up your development environment using Xcode. The structure of this session includes an introduction to the language itself, steps to configure Xcode, and creating your first project. Objective-C remains a cornerstone for developing native applications on Apple platforms, offering a unique blend of performance and flexibility that has powered countless apps over the years. Whether you're building for iOS, macOS, or even legacy systems, understanding Objective-C provides a strong foundation for working within Apple's ecosystem. Objective-C is a powerful programming language that extends the C language with object-oriented capabilities. Developed by Apple, it has been the primary language for macOS and iOS development for decades. What sets Objective-C apart is its dynamic runtime, which allows for features like message passing and runtime modifications. This dynamic nature makes it highly flexible, enabling developers to adapt and extend code at runtime. Additionally, Objective-C maintains the efficiency of C while adding high-level abstractions, making it ideal for building complex applications. Its use in frameworks and native app development has made it a critical tool for many Apple developers. One of the defining characteristics of Objective-C is its dynamic typing system, which allows variables to hold objects of any type at runtime. This contrasts with static typing found in languages like C++. The messaging system in Objective-C, where methods are called using square brackets, provides a unique way to interact with objects. Another key feature is its support for core object-oriented principles such as inheritance, polymorphism, and encapsulation, which help organize code effectively. Additionally, the runtime flexibility of Objective-C allows advanced techniques like method swizzling, where developers can swap method implementations at runtime. This makes it possible to modify behavior without altering source code, a powerful tool for debugging and extending functionality. Finally, Objective-C's ability to seamlessly integrate with C and C++ code ensures compatibility with a wide range of existing libraries and systems. Xcode is the official integrated development environment for Apple platforms, offering a comprehensive set of tools to build, test, and debug applications. It includes a code editor for writing Objective-C code, a debugger to step through your program, and an interface builder for designing user interfaces visually. Xcode also provides simulators for testing apps on various device configurations without needing physical hardware. Whether you're working on a command line tool or a full-featured app, Xcode serves as the central hub for development. Importantly, it supports both Objective-C and Swift, allowing developers to work with either language depending on their project's needs. To get started, download Xcode from the Mac App Store. Once installed, open Xcode and navigate to the Preferences menu to install the command line tools, which are essential for compiling and running code from the terminal. You can verify the installation by opening Terminal and typing Xcode select print path, which should display the installation directory. Configuring your workspace involves setting up project settings, such as the build location and compiler options. These steps ensure that your development environment is ready to handle both simple and complex Objective-C projects. Creating a new project in Xcode is straightforward. Start by opening Xcode and selecting the Create a New Xcode Project option. Choose between templates like Command Line Tool for basic programs or App for full-featured applications. When setting up the project, specify the name, select Objective-C as the language, and choose a save location. Once created, the project structure will include files like mainem, which serves as the entry point for the program, and appdelegateH and appdelegatem, which manage the application's lifecycle. Understanding this structure is crucial for navigating and modifying your code effectively. The Xcode interface is designed to streamline development. The navigator pane on the left helps you manage files, symbols, and breakpoints. The editor area is where you write and modify code or design user interfaces. The debug area provides real-time feedback, such as console output and variable values, to help identify issues. The utility pane on the right contains inspectors and libraries for customizing UI elements and configuring project settings. Familiarizing yourself with these components will make your workflow more efficient and intuitive. The basic structure of an Objective-C program begins with import directives, which include header files to access classes and functions. Classes are defined using at interface for the declaration and at implementation for the implementation. The main function acts as the entry point, similar to other C-based languages. However, Objective-C uses a unique message passing syntax where methods are called using object method. This approach allows for dynamic method resolution and enhances flexibility. Understanding these elements is essential for writing and organizing Objective-C code effectively. In summary, Objective-C is a powerful and flexible language that has been instrumental in developing Apple's ecosystem. Xcode provides the necessary tools to create, test, and debug Objective-C applications efficiently. Today's session covered the foundational concepts and setup steps required to begin your journey with Objective-C. In the next session, we will delve deeper into object-oriented programming principles, exploring how to design and implement classes, manage inheritance, and leverage polymorphism to build robust applications. Stay tuned for more insights and practical examples. Objective-C programs are organized using two primary file types. The M files contain the implementation of classes, while the H files define their public interfaces. This separation allows for clear modularity and reusability. Class definitions begin with the @interface directive, followed by the class name and any inherited classes, and conclude with @end. Method implementations are enclosed within @implementation and @end blocks, where the actual code for the methods is written. Every Objective-C program has a main function, which serves as the entry point for execution, similar to other C-based languages. This structure ensures that the program's logic is well organized and easy to maintain. In Objective-C, variables can be categorized into basic types and object types. Basic types include integers, floating point numbers, Boolean values, and characters, which are similar to those found in C object types, such as id, NSString, NSNumber, and NSArray, allow for more complex data handling and dynamic behavior. To declare properties, the @property syntax is used, which automatically generates getter and setter methods. For example, at property non-atomic, strong NS string name defines a property that is strongly referenced and not thread safe. Before the introduction of automatic reference counting, developers had to manually manage memory using retain, release, and auto-release, which required careful attention to avoid memory leaks or crashes. Methods in Objective-C are defined with either a minus sign for instance methods or a plus sign for class methods. For example, void run indicates an instance method that returns nothing, while plus void print info represents a class level method. The message sending syntax, receiver message, is a fundamental aspect of Objective-C, where an object receives a message and executes the corresponding method. This dynamic approach allows for flexibility, as the method to be called is determined at runtime. An example of this is myObject-DoSomethingWith parameter, where the receiver is myObject and the message is DoSomethingWith with a parameter. This syntax enables powerful features like method swizzling and dynamic dispatch. Classes in Objective-C are defined using the @interface directive, which typically inherits from NSObject, the root class. For instance, @interface class name, NSObject specifies that the class is a subclass of NSObject. Objects are created by calling the alloc method followed by init, as in class name object equals class name alloc init. This process allocates memory and initializes the object state. Accessors, such as getters and setters, allow interaction with an object's properties. For example, object property retrieves the value, while object property equals value assigns a new value. Inheritance is achieved by specifying a superclass in the @interface declaration, enabling code reuse and hierarchical organization. Control structures in Objective-C include conditional statements like if, else, and switch, which allow for decision-making in code. Loops such as for, while, and do while enable repeated execution of blocks of code. The for in loop is particularly useful for iterating over collections like arrays or dictionaries, simplifying the process of accessing each element. Logical operators, including and are used to combine or negate conditions. These structures form the backbone of program flow, allowing developers to create complex logic and handle various scenarios efficiently. Understanding these elements is crucial for writing effective and readable code. Objective-C emphasizes object-oriented design, making it a powerful language for building robust applications. The use of headers and implementations ensures that code is modular and easier to manage. Methods and messages are central to how objects interact, enabling dynamic and flexible behavior. A solid grasp of variables, data types, and control structures is essential for any developer working with this language. These foundational concepts not only streamline the development process, but also contribute to the creation of scalable and maintainable software. Mastery of these elements is key to becoming proficient in Objective-C. Variables serve as temporary storage locations in a computer's memory, allowing programs to hold and manipulate data while they run. Think of them as labeled boxes where you can store values that your code will use later. Each variable must have a specific type, which defines what kind of data it can hold, a unique name to identify it, and a value that it currently stores. For example, the line int age equals 25 creates a variable called age that can hold integer values and assigns it the value 25. This simple declaration is the foundation of how programs handle data dynamically. Objective-C provides a variety of data types to handle different kinds of information. Primitive data types like integers, floating point numbers, and characters are the building blocks for basic data handling. For more complex needs, Objective-C includes object types such as NS-string for text and NS-number for numeric values wrapped in objects. The choice of data type affects how much memory a variable uses and what operations can be performed on it. Selecting the appropriate type ensures that your program runs efficiently and avoids errors caused by incompatible data. Let's explore the primitive data types in Objective-C. Integers, denoted by int, store whole numbers like 10 or -5. Floats and doubles are used for decimal numbers, with float offering single precision and double providing double precision for greater accuracy. Characters, represented by char, hold single letters or symbols like A. The BOOL type is unique to Objective-C and can only hold yes or no, making it ideal for logical conditions. These types form the core of data manipulation in the language. When working with more complex data, Objective-C relies on object types. NS-string is used to represent strings, such as hello, and provides methods for string manipulation. NS number allows numeric values like 10 to be stored as objects, which is useful when working with collections. Arrays and dictionaries, like NS Array and NS Dictionary, store multiple objects, enabling structured data handling. Since objects are dynamically allocated, they require careful memory management to avoid leaks or crashes. Declaring and initializing variables follows a straightforward syntax. The basic form is data type variable name equals value. For example, float price equals 19.99 creates a floating point variable named price with the value 19.99. You can declare multiple variables in a single line by separating them with commas, like int a equals 1, b equals 2. In Objective-C, memory management is critical, so the @autoreleasable keyword is used to manage the life cycle of objects, ensuring they are released when no longer needed. Variables in Objective-C have different scopes and lifetimes depending on where they are declared. Local variables exist only within the method or block they are declared in and are destroyed once the method finishes. Instance variables are part of a class and persist as long as the object exists. Global variables declared outside methods are accessible throughout the program, but should be used sparingly. The static keyword can restrict a variable's scope to a single file, improving encapsulation and reducing potential conflicts. Constants and literals provide fixed values that do not change during program execution. You can define constants using the const keyword, like const int max equals 100, or with preprocessor directives such as define max 100. Literals are direct values like 10, 3.14, or hello, which are embedded directly into the code. Objective-C uses the @ symbol to denote object literals, such as at 10 for an NS number, or at yes for a BOOL. These features make code more readable and efficient. Adhering to best practices ensures your code is clear, maintainable, and less error-prone. Use descriptive variable names like student name instead of vague names like S. Avoid global variables unless absolutely necessary, as they can lead to unpredictable behavior. Prefer object types for complex data structures, as they offer more flexibility. Always initialize variables to prevent undefined values, which can cause crashes or logical errors. These habits will make your code easier to understand and debug. In summary, variables and data types are essential to writing effective Objective-C programs. Understanding the differences between primitive and object types, along with proper declaration and scope management, ensures your code is both efficient and reliable. By following best practices and experimenting with different data structures, you can build robust applications. Remember to always think about how data is stored, accessed, and managed to create clean and maintainable code. Control structures are the foundation of programming logic. They determine how a program flows and executes instructions. By using control structures, you can make decisions, repeat tasks, and manage the sequence of operations. These elements are crucial for creating dynamic applications where the program responds to different inputs and scenarios. Without control structures, programs would run in a linear, unchanging manner, limiting their functionality and adaptability. If statements allow you to execute specific code blocks based on whether a condition is true or false, the syntax is straightforward. You write if followed by a condition in parentheses, then the code to execute in curly braces. For example, checking if a person is old enough to vote can trigger a message. Nested conditions can handle more complex scenarios, such as validating multiple criteria simultaneously. Always ensure conditions are clear and concise to avoid logical errors. When you have multiple conditions to check, else if clauses provide a way to evaluate additional possibilities after an initial if statement. The else clause acts as a default option if none of the previous conditions are met. This structure is ideal for scenarios like grading systems, where different ranges of scores require distinct responses. Properly ordering else if statements ensures the correct logic is applied, and the else clause serves as a safety net for unexpected cases. Switch case statements are useful for evaluating a single variable against multiple possible values. You start with the switch keyword, followed by the expression to check. Each case represents a value, and the corresponding code runs if the expression matches. The default case handles any unmatched values. However, in Objective-C, switch statements only work with integer or enumeration types, so they are not suitable for strings or floating point numbers. Always include a break statement after each case to prevent unintended fall-through. Loops are essential for repeating code blocks efficiently. The for loop is ideal when you know how many times to repeat an action, such as iterating through an array. The while loop continues executing as long as a condition remains true, making it suitable for scenarios where the number of iterations is unknown. The do-while loop guarantees at least one execution, even if the condition is false from the start. Choosing the right loop type depends on the specific requirements of your program. Break and continue statements give you precise control over loop execution. The break statement exits a loop or switch block immediately, which is useful for terminating a loop once a condition is met. The continue statement skips the current iteration and moves to the next one, helping to optimize performance by avoiding unnecessary code. These tools are vital for managing complex loops and ensuring your program behaves as intended. Logical operators allow you to combine multiple conditions in a single statement. The AND operator ensures all conditions are true. The OR operator requires at least one to be true, and the NOT operator inverts a condition. For instance, checking if a user is both old enough and has a valid license uses the AND operator. Understanding operator precedence is critical to avoid unexpected results. So using parentheses to clarify complex expressions is a best practice. Writing clean and maintainable code requires following best practices for control structures. Keep conditions simple and readable by breaking them into smaller parts if necessary. Always use curly braces for code blocks, even if they contain a single line, to prevent errors when modifying code later. Avoid deep nesting by restructuring logic if needed, and test edge cases such as zero values or extreme inputs to ensure your program handles all scenarios gracefully. Control structures are the building blocks of dynamic and efficient programming. Mastering if statements, switch cases, and loops enables you to create programs that adapt to different situations. Combining these with logical operators allows for sophisticated decision-making. By following best practices, you ensure your code remains readable, reliable, and easy to maintain. These concepts are fundamental to solving real-world problems and writing high-quality Objective-C applications. Functions and methods are essential for organizing code in Objective-C. They allow programmers to break down complex tasks into manageable pieces. Functions are standalone blocks of code, meaning they exist independently of any class or object. In contrast, methods are tied to classes and objects, making them an integral part of object-oriented programming. Both functions and methods enable code reuse and modularity, which are crucial for building scalable and maintainable applications. By using functions and methods, developers can avoid duplicating code, making their programs more efficient and easier to update. Functions are C-style routines defined with a return type and parameters. For example, a function named addNumbers takes two integers as input and returns their sum. This is a simple way to encapsulate a specific task, such as performing calculations or handling data. Functions are used for general-purpose tasks that do not require access to object-specific data. They are particularly useful for utility operations, like mathematical computations or string manipulations, which can be reused across different parts of an application. Since functions are not tied to any class, they operate in a stateless manner, making them ideal for tasks that do not depend on the internal state of an object. Methods are functions defined within a class and called on instances of that class. For example, a method named printMessage might display a message using the nslog function. Methods are part of the class's interface and are used to define the behavior of objects. Unlike functions, methods have access to the instance variables and other methods of the class, allowing them to interact with the object's data. This makes methods a fundamental part of object-oriented programming, as they enable objects to perform actions based on their own state. By encapsulating behavior within a class, methods promote data hiding and modular design, which are key principles of OOP. The key differences between functions and methods lie in their scope and capabilities. Functions are standalone and do not have access to object state, meaning they cannot directly interact with an object's data or other methods. Methods, on the other hand, are part of a class and can access instance variables and call other methods, making them ideal for tasks that involve object-specific behavior. In terms of syntax, functions use a return type followed by a function name and parameters, while methods use a hyphen or plus sign to indicate instance or class methods, respectively. This distinction in syntax reflects their different roles within the language, with methods being tightly integrated into the object model. The syntax for methods in Objective-C uses a hyphen or plus sign to denote instance or class methods. For example, An instance method starts with a hyphen, followed by the return type, method name, and parameters. Parameters are specified using colon notation, which provides clarity and flexibility. This approach allows for more descriptive method names, as each parameter is explicitly labeled. For instance, a method named calculate_area with radius takes a double value as input and returns a double. The colon notation makes it easier to understand the purpose of each parameter, especially when a method has multiple arguments. This feature is unique to Objective-C and enhances readability in method calls. A function like calculate_area takes a radius as input and returns the area of a circle. This is a straightforward, stateless operation that does not rely on any object. In contrast, a method like calculate_area would be part of a class and could access the object's properties, such as its radius. The function is called directly, while the method is invoked on an instance of the class. This distinction highlights how functions and methods serve different purposes in the language. Functions are ideal for general tasks, while methods are used to define behavior that is specific to an object state, making them essential for object-oriented design. Best practices for functions and methods include using functions for tasks that do not require access to object state and methods for operations that involve an object's data. Functions should be kept simple and focused on a single task, while methods should encapsulate behavior that is relevant to the class they belong to. Naming conventions are also important, with functions typically using lowercase names and methods using verbs to describe their actions. For example, a method named drawCircle clearly indicates its purpose. Following these guidelines ensures that code remains organized, readable, and maintainable, which is critical for large-scale applications. In summary, functions and methods are vital tools in Objective-C for structuring code and implementing functionality. Functions provide a way to modularize general tasks, while methods enable objects to interact with their own data and perform actions. Understanding the differences between them and using them appropriately is essential for writing efficient and maintainable code. By adhering to best practices, such as clear naming and proper encapsulation, developers can create robust applications that are easy to update and scale. Whether working with functions or methods, the goal is to build a clean, organized code base that reflects the principles of object-oriented programming. Arrays in Objective-C serve as fundamental structures for organizing and managing collections of objects. They allow you to store multiple elements in an ordered sequence, which can be of the same or different types. This makes them incredibly useful for handling data in a structured way. The two primary types of arrays in Objective-C are NS array and NS mutable array. NS array is immutable, meaning once it is created, its contents cannot be changed. This is ideal for scenarios where data remains constant, such as configuration settings or predefined lists. On the other hand, NS mutable array is mutable, allowing you to dynamically add, remove, or modify elements during runtime. This flexibility is essential for applications that require frequent data updates, such as user input processing or real-time data tracking. Understanding the distinction between these two types is crucial for effective data management in your programs. Immutable arrays, known as NS array, are designed to hold data that does not change after creation. This immutability ensures that the data remains consistent, which is particularly valuable in scenarios where read-only access is required. For example, if you have a list of country names or a set of predefined constants, using an NS array prevents accidental modifications. To create an NS array, you can use methods like array with objects, which takes a list of objects followed by a nil terminator. For instance, the code NS array names equals NS array with objects @Alice, @Bob, nil creates an array containing two strings. Once created, you can retrieve elements using methods like object@index, or determine the number of elements with the count property. Since the contents of an NS array cannot be altered, it is a safer choice for data that should remain unchanged throughout the program's execution. Mutable arrays, or NS mutable array, offer the ability to modify their contents dynamically. This makes them suitable for situations where data needs to evolve during runtime, such as maintaining a list of user-generated items or updating a shopping cart. You can add objects using addObject, or insert them at specific positions with insertObject @index. Removing elements is also straightforward with methods like removeObject or removeObject @index. For example, the code NS mutable array numbers equals NS mutable array initializes an empty mutable array, which can later be populated with numbers or other objects. flexibility of NS mutable array comes with the responsibility of managing changes carefully to avoid unintended side effects. This type of array is particularly useful in applications where data is frequently modified, such as in game development or interactive user interfaces. Creating arrays in Objective-C involves using specific class methods that cater to both immutable and mutable types. For NS array, you can use array with objects to initialize an array with a list of objects, ensuring you terminate the list with nil. Another method, array with array, allows you to create a new array based on an existing one. For NS mutable array, the array method creates an empty mutable array, while array with capacity initializes it with a specified capacity for efficiency. Additionally, the init with objects initializer provides a way to customize the array's contents during creation. It is crucial to remember that array with objects requires a nil terminator to signal the end of the object list, as failing to do so can lead to runtime errors. Choosing the right method depends on your specific needs, whether you are creating a static list or preparing for dynamic modifications. Accessing elements in an array is a common task in Objective-C programming. The object@index method allows you to retrieve a specific element by its index, which starts at 0. For example, if you have an array of names, names 0 would give you the first element. The count property provides the total number of elements in the array, which is useful for iterating through the collection. To check if an array contains a particular object, you can use contains object, which returns a Boolean value. Additionally, index of object helps you find the position of a specific object within the array. These methods are essential for tasks like searching for data, validating input, or performing operations on individual elements. Always ensure that the index you are accessing is within the valid range to avoid out-of-bounds errors, which can cause crashes or undefined behavior. Objective-C arrays come with a variety of methods to manipulate and process their contents. For NS array, the sorted array using selector method allows you to sort the array based on a specific selector, such as comparing strings alphabetically or numbers numerically. The components joined by string method is useful for concatenating all elements of an array into a single string, separated by a specified delimiter. On the other hand, NS mutable array provides methods like addObject to append elements to the end of the array, removeObject to remove a specific object, and insert object at index. To add an object at a specific position. These methods enable you to dynamically manage data, making it easier to handle scenarios like updating a list of tasks or reordering items in a user interface. Familiarizing yourself with these methods enhances your ability to work with arrays effectively. Adhering to best practices when working with arrays ensures cleaner and more reliable code. For static data that does not change, always use NSArray to enforce immutability and prevent accidental modifications. When dealing with data that requires frequent updates, opt for NSMutable array to take advantage of its flexibility. Before accessing array elements, check for nil to avoid runtime errors, especially when dealing with optional or dynamically generated data. When passing arrays to other parts of your code, consider using the copy method to create a snapshot of the array, preventing unintended changes to the original data. These practices not only improve code stability, but also make it easier to debug and maintain. By following these guidelines, you can leverage the full potential of arrays while minimizing common pitfalls. In conclusion, arrays are a cornerstone of data management in Objective-C, providing a structured way to handle collections of objects. Understanding the difference between immutable NSArray and mutable NSMutable array is essential for choosing the right tool for your task. Whether you need to store static data or manage dynamic information, arrays offer the flexibility and efficiency required for various programming scenarios. Mastering the methods for creating, accessing, and modifying arrays empowers you to write more effective and maintainable code. As you continue exploring Objective-C, remember that arrays are not just a technical feature, but a fundamental concept that underpins many aspects of software development. With practice and attention to best practices, you will become proficient in using arrays to solve real-world problems. Dictionaries and sets are fundamental collections in Objective-C. They play a crucial role in organizing and managing data efficiently within object-oriented programming. Dictionaries specifically store key-value pairs, allowing you to map unique keys to corresponding values. This makes them ideal for scenarios where you need to quickly retrieve data based on a specific identifier. On the other hand, sets store unique, unordered objects, ensuring that no duplicates exist within the collection. This characteristic makes sets particularly useful for tasks like checking membership. or eliminating redundant entries. Both structures are essential tools for developers to handle data in a structured and optimized manner. To create dictionaries in Objective-C, you can use the NS Dictionary class for immutable instances, which means their contents cannot be modified after initialization. For example, you can initialize an NS dictionary with a literal syntax like NS Dictionary dict equals at key 1, at value 1, at key 2, at value 2. This approach provides a concise way to define key-value pairs. For mutable dictionaries, the NS Mutable Dictionary class is used, allowing you to add, remove, or update entries dynamically. A common way to initialize an empty mutable dictionary is through the class method NS Mutable Dictionary Dictionary, which returns an instance ready for modifications. Understanding the distinction between immutable and mutable collections is vital for managing data flexibility in your applications. Accessing and modifying dictionary elements involves using specific methods provided by the NS Dictionary and NS Mutable Dictionary classes. To retrieve a value, you can use the object for key method, passing the key as an argument. For example, dict object for key at key 1 returns the value associated with key 1. When working with mutable dictionaries, you can update values using the setObject4key method, such as mutable dict setObject at new value for key at key 1, which replaces the existing value or adds a new key value pair. Removing entries is equally straightforward with the removeObject4key method, which deletes the specified key and its corresponding value. These operations enable precise control over dictionary contents during runtime. Creating and initializing sets in Objective-C requires the use of NSSet for immutable instances and NSMutableSet for mutable ones. To create an immutable set, you can use the setWithObjects method, passing the objects you want to include followed by a nil terminator. For example, NSSetSet equals NSSet setWithObjects at A, at B, nil. This ensures the set contains unique elements and maintains no specific order. For mutable sets, the NSMutableSet class provides methods to add or remove objects dynamically. Initializing an empty mutable set is done with NSMutableSetSet, which creates an instance that can be modified later. Sets are particularly useful when you need to enforce uniqueness and perform quick membership checks. Accessing and modifying set elements involves methods that check for object presence and allow additions or removals. The contains object method is used to verify if a specific object exists in the set, returning a Boolean value. For example, set contains object at A checks whether O is present. When working with mutable sets, you can add objects using the addObject method, such as mutable set addObject at C, which ensures the object is included only once. Removing objects is achieved with the removeObject method, which deletes the specified object if it exists. These operations make sets a powerful tool for managing collections where duplicates are not allowed. Dictionaries offer several common methods to interact with their contents. The AllKeys method returns an array containing all the keys in the dictionary, which can be useful for iterating over keys or performing lookups. The AllValues method retrieves an array of all the values, providing a way to access the stored data without referencing keys. The ObjectForKey method is used to fetch a specific value based on its key, making it a fundamental operation for data retrieval. Additionally, the count method returns the number of key value pairs in the dictionary, offering a quick way to determine its size. These methods collectively enhance the functionality of dictionaries in managing and analyzing data. Sets also have a set of common methods for interacting with their elements. The count method returns the number of objects in the set, similar to dictionaries, but for individual elements. The contains object method checks whether a specific object is present, which is efficient for membership testing. The addObject method allows you to add a new object to the set, ensuring it is unique. The removeObject method deletes an existing object from the set. These methods make sets a reliable choice for tasks requiring uniqueness and quick lookups, such as managing user roles or filtering data. Practical examples highlight the real-world applications of dictionaries and sets. Dictionaries are ideal for mapping usernames to unique identifiers, such as user IDs, allowing for quick lookups and data organization. Sets, on the other hand, are perfect for storing unique user roles, ensuring no duplicates exist in the collection. Combining these structures with loops enables bulk operations, such as iterating over all keys in a dictionary or processing each element in a set. For instance, you might loop through a dictionary's keys to generate reports, or use a set to track active sessions. These examples demonstrate how dictionaries and sets can be leveraged to solve common programming challenges efficiently. Dictionaries and sets are essential tools for organizing and managing data in Objective-C dictionaries. Excel in scenarios requiring key-value relationships, such as configuration settings or data mapping. Sets, with their focus on uniqueness and unordered storage, are invaluable for tasks like membership checks or data filtering. Mastering their methods allows developers to write more efficient and readable code, improving both performance and maintainability. By understanding when to use each structure, you can optimize your applications and handle complex data interactions with ease. Object-oriented programming, or OOP, is a programming paradigm that revolves around the concept of objects and classes. These objects are like real-world entities that encapsulate data and behavior. OOP is built on 4 fundamental principles, which are encapsulation, inheritance, polymorphism, and abstraction. Encapsulation refers to the bundling of data and methods that operate on that data within a single unit called a class. Inheritance allows a class to inherit properties and methods from another class, creating a hierarchical relationship. Polymorphism enables objects to take on many forms, often through method overriding, where a subclass provides a specific implementation of a method defined in its superclass. Abstraction simplifies complex systems by hiding unnecessary details and exposing only essential features. Objective-C leverages these OOP principles to create modular and reusable code, making it easier to manage large-scale applications. By organizing code into classes and objects, developers can build scalable solutions that are easier to maintain and extend over time. A class in Objective-C serves as a blueprint for creating objects. It defines the properties and methods that an object of that class will have. For example, when you declare a class using the @interface keyword, you are specifying its structure. An object, on the other hand, is an instance of a class. When you create an object, you are essentially generating a specific entity based on the class blueprint. In Objective-C, you create an object using the alloc and init methods, such as myClassAllocInit, which allocates memory for the object and initializes its properties. Classes contain properties, which are variables that hold data, and methods, which are functions that define the behavior of the object. This separation of structure and instance allows for efficient code organization and reuse. By defining a class once, you can create multiple objects that share the same structure but hold different data, making it a powerful tool for managing complex applications. Inheritance is a key feature of OOP that allows a class to inherit properties and methods from another class. The class that is inherited from is called the base class or superclass, while the class that inherits is known as the derived class or subclass. This relationship enables code reuse and promotes a hierarchical structure. For example, if you have a superclass called vehicle, you can create a subclass called car that inherits all the properties and methods of vehicle while adding its own unique features. In Objective-C, inheritance is implemented using the colon symbol in the class declaration, such as at interface subclass, superclass. This allows the subclass to build upon the functionality of the superclass, reducing redundancy and making the code more maintainable. Inheritance also supports the concept of generalization, where common attributes and behaviors are grouped into a superclass, and specific details are handled in subclasses. Encapsulation is the practice of hiding the internal state of an object and restricting direct access to its data. Instead, interactions with the object occur through well-defined methods. This approach enhances security and prevents unintended modifications to the data. In Objective-C, encapsulation is achieved using properties and the @synthesize directive. Properties allow you to declare variables with specific access levels, such as read-only or read-write. The @synthesize keyword automatically generates the getter and setter methods for these properties, ensuring that any changes to the data are controlled. For instance, if a property is marked as read-only, it can only be set during initialization, preventing external code from altering it afterward. This level of control is crucial for maintaining the integrity of an object's data, especially in scenarios where certain values must remain consistent throughout the object's life cycle. Encapsulation also simplifies the design of complex systems by allowing developers to focus on the public interface of an object rather than its internal implementation. Polymorphism is the ability of objects to take on multiple forms, allowing a single interface to represent different underlying forms. In Objective-C, this is primarily achieved through method overriding where a subclass provides a specific implementation of a method that is already defined in its superclass. For example, if a superclass has a method called draw, a subclass can override this method to provide a unique implementation tailored to its specific needs. This flexibility is made possible by Objective-C's dynamic binding, which determines the correct method to call at runtime based on the object's actual type. Polymorphism enables developers to write more generic and reusable code, as they can work with objects through a common interface without needing to know their specific subclass types. This feature is particularly useful in scenarios where different classes need to respond to the same message in their own way, promoting a more adaptable and scalable code base. Message passing is a core mechanism in Objective-C that allows objects to communicate by sending messages to each other. Unlike traditional function calls, where the method is resolved at compile time, Objective-C uses a dynamic approach where the method is determined at runtime. The syntax for sending a message is receiver message, where the receiver is the object that receives the message, and the message is the method to be invoked. For example, object do something sends the do something message to the object, triggering the corresponding method. This dynamic nature of message passing provides significant flexibility, as it allows for late binding and the ability to change behavior at runtime. It also supports features like method swizzling, where the implementation of a method can be replaced dynamically. This runtime flexibility makes Objective-C a powerful language for building applications that require adaptability and extensibility. In conclusion, object-oriented programming in Objective-C offers a structured and efficient way to develop applications. The principles of classes, inheritance, encapsulation, and polymorphism form the foundation of this approach, enabling developers to create modular, reusable, and scalable code. By organizing code into classes and objects, developers can manage complexity more effectively, making it easier to maintain and extend applications over time. Inheritance allows for code reuse and hierarchical organization, while encapsulation ensures data integrity and security. Polymorphism and message passing add flexibility, allowing objects to adapt to different scenarios dynamically. Mastering these concepts is essential for anyone looking to become proficient in Objective-C. as they underpin the language's ability to handle complex software development tasks. With practice and a solid understanding of these principles, developers can build robust and maintainable applications that meet the demands of modern software development. Classes serve as blueprints that define the structure and behavior of objects. Think of a class as a template that outlines what data an object can hold and what actions it can perform. Objects, on the other hand, are the actual instances created from these blueprints. In Objective-C, this approach helps organize code and data into manageable, reusable components. The core principles of object-oriented programming, which Objective-C emphasizes, include encapsulation, inheritance, and polymorphism. Encapsulation allows data to be hidden and accessed through controlled methods. Inheritance enables classes to build upon existing ones, and polymorphism lets objects of different classes respond to the same message in unique ways. These principles form the foundation of structured and scalable software development. To define a class in Objective-C, we use the @interface directive. The syntax begins with @interface class name, NSObject, where NSObject is the root class in the Objective-C hierarchy. This line declares the class name and its superclass. Within the interface block, we declare properties and methods that the class will expose. Properties are variables that store data, while methods define the actions the class can perform. Once the interface is defined, the actual implementation of methods is written in the @implementation block. This separation of interface and implementation is a key feature of Objective-C, promoting modularity and clarity in code structure. Properties in Objective-C are declared using the @property keyword, which automatically generates getter and setter methods. For example, @property NSStringName creates a property named name that can store a string value. These properties act as the data members of a class, holding the state of an object. Methods, on the other hand, define the behavior of a class. A method like void greet specifies an action that an object can perform. The @synthesize directive was traditionally used to generate the underlying code for these properties. But modern Objective-C automatically synthesizes them. When accessing properties, you can use self-property name to invoke the getter or setter, or directly reference property name for faster access. Though the former is generally preferred for consistency and encapsulation, Creating an object in Objective-C involves allocating memory and initializing the instance. The standard syntax is class name alloc init, where alloc reserves memory and init sets up the object's initial state. For example, person equals person alloc init creates a new person object. Objects can be stored in variables, added to collections like arrays or dictionaries, or passed between methods. Memory management in Objective-C has evolved over time, while manual reference counting with retain and release was once required. Modern projects typically use automatic reference counting arc, which handles memory management automatically. This reduces the risk of memory leaks and simplifies code maintenance. Initialization is a critical step in object creation, where the object's properties are set to their initial values. The init method is the default initializer, but custom initializers can be defined to accept parameters. For instance, instance set type init with name, ns string name, allows a person object to be created with a specific name. When writing custom initializers, it's essential to call self-super init first to ensure the superclass is properly initialized. This step is crucial for maintaining the integrity of the inheritance chain. After that, you can assign values to properties or perform any additional setup required for the object to function correctly. In Objective-C, objects communicate by sending messages to each other. The syntax object method sends a message to the object to invoke the method. For example, person greet calls the greet method on a person instance. This messaging system is dynamic, meaning that the actual method to be executed is determined at runtime. This flexibility allows for techniques like method swizzling, where methods can be replaced or modified after compilation. Another powerful feature is perform selector, which enables indirect method calls by passing a selector as a parameter. This is particularly useful in scenarios requiring dynamic behavior, such as handling user input or implementing plugins. Inheritance in Objective-C allows a class to inherit properties and methods from another class, known as the superclass. This is achieved by declaring the subclass with that interface subclass, superclass. For example, a student class might inherit from a person superclass, gaining access to all its properties and methods. Subclasses can override methods to provide their own implementation, which is done by redeclaring the method in the subclass. When overriding, it's common to call the superclass's version of the method using super, ensuring that the original behavior is preserved while adding or modifying functionality. This mechanism supports code reuse and promotes a hierarchical structure in software design. Encapsulation is the practice of hiding an object's internal data and exposing only necessary functionality through methods. In Objective-C, this is achieved by declaring properties as private within the @implementation block rather than the @interface. By doing so, external code can only interact with the object through its public methods, which act as gatekeepers for the data. For example, a bank account class might have a private balance property with public methods like deposit and withdraw to modify it. This protects the data from unintended changes and ensures that any modifications adhere to specific rules or validations. Encapsulation enhances security, reduces complexity, and makes code easier to maintain and extend. Classes and objects are the cornerstone of Objective-C programming, enabling developers to model real-world entities and interactions in code. By mastering object-oriented principles like encapsulation, inheritance, and polymorphism, you can create modular, reusable, and scalable applications. Practice defining classes, initializing objects, and leveraging methods to build robust solutions. As you progress, explore advanced concepts like inheritance to create hierarchical relationships and encapsulation to protect data integrity. These skills will not only improve your code structure, but also empower you to design more sophisticated and efficient software systems. Keep experimenting and refining your understanding to unlock the full potential of Objective-C. Inheritance and polymorphism are foundational pillars of object-oriented programming. In Objective-C, inheritance allows classes to inherit properties and methods from other classes, creating a hierarchical structure that promotes code reuse. This means you can define a general class, such as an animal, and then create more specific classes like dogs or cats that inherit the animal's characteristics while adding their own unique behaviors. Polymorphism, on the other hand, enables objects of different classes to be treated as objects of a common superclass. This flexibility allows a single interface to represent various underlying forms, making it easier to manage complex systems where different objects can respond to the same message in their own way. Together, these concepts form the backbone of OOP in Objective-C, providing a structured yet adaptable approach to software development. In Objective-C, inheritance is declared using the syntax at interface class name, superclass name. This notation explicitly defines a subclass that inherits from a superclass, allowing the subclass to access the superclass's properties and methods. For example, a dog class can inherit from an animal class, gaining access to shared attributes like age or name, as well as methods like eat or sleep. Subclasses can also override methods from the superclass by defining a method with the same name, but a different implementation. This process, known as method overriding, allows for customization of behavior while maintaining a consistent interface. The example of at interface dog animal demonstrates how this hierarchical relationship enables the creation of specialized classes that build upon existing functionality, reducing redundancy and improving code organization. Objective-C supports single inheritance, meaning a class can inherit from only one superclass. This design choice simplifies the class hierarchy and avoids the complexities that come with multiple inheritance. However, it also encourages a clear and focused design where each class has a single responsibility. Method overriding is a key aspect of inheritance, allowing subclasses to provide their own implementation of a method defined in the superclass. This is particularly useful for tailoring behavior to specific needs, such as having a dog class override the make sound method to bark instead of the generic animal sound. Access control mechanisms like at protected, at private, and at public further refine inheritance by determining how properties and methods are accessed within the class hierarchy. These controls ensure that sensitive data remains encapsulated while allowing necessary interactions between classes. Polymorphism in Objective-C allows a single interface to represent different underlying forms, enabling objects of various classes to be treated as instances of a common superclass. For instance, an animal pointer can reference a dog or cat object, and when the make sound method is called, the actual object's implementation determines the behavior. This dynamic behavior is facilitated by dynamic method dispatch, a feature of Objective-C that resolves method calls at runtime rather than compile time. This flexibility means that the same method can behave differently depending on the object's type, making the code more adaptable and scalable. Polymorphism is particularly powerful in scenarios where you need to handle a collection of objects uniformly, such as iterating through a list of animals and allowing each to produce its unique sound. Implementing polymorphism in Objective-C involves checking the type of an object at runtime to determine how it should be handled. Methods like isKindOfClass and isMemberOfClass allow developers to verify the class of an object, ensuring that operations are performed correctly. For example, if you have an animal pointer that might reference a dog or cat, you can use these methods to decide which specific implementation to use. Overriding methods in subclasses is another critical aspect of polymorphism, as it allows each subclass to provide its own version of a method. This means that when the makeSound method is called on an animal pointer, the runtime selects the appropriate implementation based on the actual object type, whether it is a dog, cat, or another subclass. This approach enhances flexibility and ensures that the code can evolve without requiring changes to existing interfaces. The benefits of inheritance and polymorphism in Objective-C are profound. Inheritance promotes code reusability by allowing developers to build upon existing classes rather than writing redundant code. This not only saves time, but also reduces the likelihood of errors. Scalability is another advantage, as the hierarchical structure of inheritance makes it easier to add new features or modify existing ones without disrupting the entire system. Maintainability improves because changes to a superclass automatically propagate to all subclasses, ensuring consistency across the application. Additionally, polymorphism enables flexible and extensible designs, allowing developers to write code that can adapt to new requirements without significant rework. These concepts collectively contribute to the creation of robust, scalable, and maintainable applications, making them essential tools for any Objective-C developer. Inheritance and polymorphism are essential components of object-oriented programming in Objective-C, offering a structured yet adaptable approach to software development. Inheritance fosters code reuse by allowing classes to build upon existing functionality, while polymorphism enables dynamic behavior by treating objects of different classes as instances of a common superclass. These principles work together to create systems that are both efficient and scalable, allowing developers to manage complexity with ease. Mastering these concepts is crucial for building robust applications that can evolve with changing requirements. By leveraging inheritance and polymorphism, developers can create code that is not only reusable, but also flexible, ensuring that their applications remain maintainable and extensible over time. Memory management in Objective-C involves controlling the lifetimes of objects to ensure efficient use of system resources. This process is fundamental to preventing issues like memory leaks and crashes, which can degrade application performance. Key concepts include ownership, which determines who is responsible for releasing an object, and reference counting, which tracks how many times an object is being used. The retain count is a numerical value that increases when an object is retained and decreases when it is released. Understanding these principles is essential for writing robust code. Manual reference counting, or MRC, requires developers to manually manage retain and release calls, while automatic reference counting, or ARC, automates this process. However, even with ARC, a solid grasp of MRC concepts is crucial for troubleshooting and optimizing memory usage. Proper memory management ensures that objects are deallocated when they are no longer needed, freeing up system resources for other tasks. Objects in Objective-C are owned by one or more references, which means their lifetimes are tied to these references. The retain count is a critical metric that tracks how many owners an object has. When an object is retained, its retain count increases by 1, signaling that it is still in use. Conversely, when an object is released, its retain count decreases by 1, indicating that an owner is no longer using it. This mechanism ensures that an object is only deallocated when its retain count reaches 0, meaning no references to it remain. The retain count is not a public property, but can be accessed via the retain count method, though it is not always reliable for debugging. Understanding ownership and references helps developers avoid common pitfalls like over-releasing or under-releasing objects. The retain and release methods are central to managing an object's lifetime. The retain method increases the retain count of an object, effectively taking ownership of it. This is often used when you need to ensure an object remains in memory for a specific duration. The release method, on the other hand, decreases the retain count, signaling that an owner no longer needs the object. When the retain count reaches 0, the object is deallocated. Another important method is auto-release, which schedules an object for release at a later time, typically when the current auto-release pool is drained. This is useful for deferring memory management tasks, especially in methods that return objects. For example, calling object retain followed by object release temporarily increases and then decreases the retain count, ensuring the object remains valid during a specific operation. Auto-release pools play a vital role in managing objects that are scheduled for release at a later time. These pools act as containers that hold auto-released objects until they are explicitly drained. When an auto-release pool is drained, all objects within it are sent a release message, reducing their retain counts. This mechanism is particularly useful in scenarios like loops, blocks, or methods that return auto-released objects. For instance, when creating an object with NS-object-alloc init, you can call auto-release to ensure it is released at the end of the current scope. Auto-release pools are often used in UI kit applications, where they help manage temporary objects created during user interactions. By deferring releases, auto-release pools help balance memory usage and prevent premature deallocation of objects. Common pitfalls in memory management can lead to serious issues if not addressed. Over-releasing occurs when an object is released more times than it has been retained, causing its retain count to drop below 0 and resulting in a crash. Retain cycles happen when 2 or more objects hold strong references to each other, creating a loop that prevents them from being deallocated. This is a frequent problem in delegate patterns or closures that capture their surrounding context. Forgetting to release objects in loops or blocks can lead to memory leaks, as the retain count never reaches 0. Additionally, misusing auto-release in performance-critical code can introduce delays, as objects are not released immediately. Developers must carefully analyze their code to identify and resolve these issues, ensuring smooth application behavior. Best practices for memory management emphasize efficiency and reliability. The first recommendation is to prefer automatic reference counting, which automates retain and release calls, reducing the likelihood of human error. However, understanding manual reference counting remains important for debugging and optimizing code. Using strong and weak references appropriately helps avoid retained cycles. Strong references indicate ownership, while weak references do not, making them ideal for scenarios where a non-owning relationship is needed. Releasing objects as soon as they are no longer needed is crucial for maintaining low memory usage. Finally, testing for memory leaks using tools like instruments is essential for identifying and fixing issues before deployment. These practices collectively contribute to writing stable and efficient Objective-C applications. Memory management is a cornerstone of efficient resource usage in Objective-C. A deep understanding of retain, release, and auto-release mechanisms ensures that objects are properly allocated and deallocated. Avoiding retained cycles and over-releasing is critical for preventing crashes and memory leaks. While automatic reference counting simplifies many aspects of memory management, developers must still grasp the underlying principles of manual reference counting to write effective code. By adhering to best practices and leveraging tools like instruments, developers can create applications that are both performant and stable. Mastering these concepts is essential for anyone seeking to build high-quality Objective-C programs. Objective-C uses manual memory management for objects, meaning developers are responsible for tracking and controlling the life cycle of each object. The key methods involved are retain, release, and auto-release, which directly affect the retain count of an object. Retain increases the count, release decreases it, and auto-release schedules a release at a later time. Understanding these mechanisms is crucial because improper management can lead to memory leaks or crashes, while proper usage ensures that resources are efficiently allocated and freed. Optimizing application performance. The retain method increases the retain count of an object, effectively granting the current owner-exclusive responsibility for its life cycle. This prevents the object from being deallocated as long as the retain count remains positive. For example, when you call object retain, you are taking ownership of that object, and it will not be destroyed until you release it. This is essential when you need to ensure an object remains available for use beyond the current scope, such as when storing it in a property or a collection. The release method decreases the retain count of an object. When the retain count reaches 0, the object is deallocated, and its memory is returned to the system. This is the primary mechanism for freeing up resources that are no longer needed. For instance, if you call object release, you are relinquishing ownership, and the object will be destroyed if no other references remain. It is critical to balance each retain with a corresponding release to avoid memory leaks or premature deallocation. The auto-release method schedules an object for release at the end of the current auto-release pool, which is a special container that manages auto-released objects. This is particularly useful when returning objects from methods, as it allows the caller to avoid immediately releasing the object. For example, when you return object auto-release, the object is added to the auto-release pool, and it will be released automatically when the pool is drained. This simplifies memory management in scenarios where ownership is transferred. Auto-release pools are containers that hold auto-released objects and release them when the pool is drained. This mechanism is fundamental in COCO applications, where objects are often created and passed around without immediate cleanup. That auto-release pool block, introduced in modern Objective-C, provides a structured way to manage these pools, ensuring that auto-released objects are released at the appropriate time. This helps prevent memory spikes and ensures that resources are freed efficiently, especially in loops or during large operations. The workflow of retain and release revolves around ownership and responsibility. When you retain an object, you take ownership, and when you release it, you give up ownership. This balance is critical because every retain must be matched with a release. For example, if you retain an object in one part of your code, you must ensure that a corresponding release occurs later. Failing to do so results in memory leaks, while over-releasing can cause crashes due to accessing deallocated memory. Auto-release and manual release serve different purposes in memory management. Auto-release defers the release of an object until the end of the current auto-release pool, making it ideal for temporary objects or return values. Manual release, on the other hand, requires immediate attention and is used when you want to free an object as soon as it is no longer needed. For instance, auto-released objects are commonly used in methods that return newly created instances, while manual release is more appropriate for objects that are no longer needed in the current scope. Common pitfalls in memory management include forgetting to release an object, which leads to memory leaks as the object remains in memory indefinitely. Over-releasing, where an object is released more times than it was retained, causes crashes due to invalid memory access. Misusing auto-release can also delay resource cleanup, leading to increased memory usage. For example, auto-releasing an object that is not needed immediately may prevent it from being freed until the pool is drained, which could impact performance if the object is large or numerous. Best practices for memory management involve balancing retain and release operations, ensuring that every retain is matched with a release. Using auto-release for objects returned from methods simplifies ownership transfer and reduces the risk of leaks. Additionally, avoiding strong reference cycles, such as when two objects retain each other, is essential to prevent memory leaks. Developers should also leverage tools like Xcode's static analyzer and instruments to detect and fix memory-related issues, ensuring code stability and efficiency. Retain, release, and auto-release are foundational to memory management in Objective-C, enabling precise control over object life cycles. Proper usage ensures that applications manage resources efficiently, avoiding leaks and crashes while maintaining performance. Mastery of these concepts is essential for writing robust and reliable code, as even small mistakes can lead to significant issues. By following best practices and understanding the underlying mechanics, developers can create applications that are both efficient and stable. Protocols in Objective-C serve as blueprints that define a set of methods, properties, and other requirements that classes can adopt. They allow different classes to share a common interface, enabling them to implement specific functionality in their own way. Unlike interfaces in some other languages, protocols in Objective-C offer more flexibility because they can be adopted by any class, and they can also be used to define optional methods. This makes protocols a powerful tool for structuring code and promoting reusable components. To define a protocol in Objective-C, you use the @protocol keyword followed by the protocol name. For example, a protocol named myProtocol might declare a required method like required method. You can also specify whether methods are required or optional using the @required and @optional directives. This distinction allows developers to create protocols that enforce certain behaviors while leaving room for customization. Protocols can be as simple or complex as needed, making them versatile for a wide range of applications. When a class wants to adopt a protocol, it lists the protocol in its interface declaration. For instance, a class named My Class can adopt My Protocol by writing My Protocol after its superclass. This tells the compiler that My Class must implement all the required methods of the protocol. If a protocol includes optional methods, the class can choose to implement them or not. This adoption process ensures that classes adhere to a consistent interface while maintaining their unique implementation details. Delegates are a fundamental pattern in Objective-C, particularly in frameworks like Cocoa and Cocoa Touch. A delegate is an object that takes on specific responsibilities for another object, effectively handing off tasks to a different instance. This allows for dynamic behavior and customization without relying on subclassing. Delegates are typically defined using protocols, which outline the methods the delegate must implement. This separation of concerns makes code more modular and easier to maintain. The delegate pattern follows a clear set of steps to enable communication between objects. First, you define a protocol that specifies the methods the delegate must implement. Next, the class that needs a delegate declares a property of type id with the protocol as its type. The delegate object then implements the required methods, and the original class calls these methods when certain events occur. This structured approach ensures that objects can interact without being tightly coupled, improving flexibility and scalability. Let's look at an example of a delegate implementation. A protocol named DataDelegate might include a method like didReceiveData, which is called when data is received. The class that uses this delegate declares a weak property to hold the delegate, preventing retain cycles. When the class needs to notify the delegate, it invokes the method on the delegate object. This pattern is widely used in scenarios like network requests or user interface updates, where one object needs to inform another of changes without direct dependencies. Protocols and delegates offer several key benefits that enhance Objective-C development. They promote code reusability by allowing multiple classes to share a common interface. They also encourage modularity by decoupling classes, making it easier to modify or replace components without affecting the rest of the code base. Additionally, the flexibility of protocols and delegates enables dynamic behavior, allowing objects to adapt to different contexts and requirements. These advantages make them essential tools for building scalable and maintainable applications. Common use cases for protocols and delegates include UI components like UI table view, where the delegate handles user interactions and data display. They are also used to customize behavior without subclassing, which reduces code duplication and complexity. For example, a custom view might use a delegate to handle events like button taps or data changes. Delegates are also crucial for event handling and callback mechanisms, providing a clean way for objects to communicate and respond to actions. To make the most of protocols and delegates, follow best practices that ensure clarity and efficiency. Keep protocols focused on a single responsibility, avoiding overly broad or generic interfaces. Use optional methods sparingly, as they can lead to unexpected behavior if not handled properly. Always declare delegate properties as weak to prevent retain cycles, which can cause memory leaks. By adhering to these guidelines, developers can create robust and maintainable code that leverages the full power of Objective-C's delegation model. In summary, protocols define the required functionality that classes must implement, while delegates enable objects to communicate and share responsibilities dynamically. Together, they form a cornerstone of Objective-C development, allowing for flexible, reusable, and well-structured code. By mastering these concepts, developers can build applications that are easier to maintain, extend, and adapt to changing requirements. Protocols and delegates are essential tools for creating modular and efficient Objective-C programs. Objective-C provides a powerful feature known as categories and extensions that allow developers to extend the functionality of existing classes without modifying their original source code. This capability is particularly useful when working with system classes, or when you want to organize methods into logical groupings. Categories and extensions serve different purposes, but both contribute to enhancing code modularity. By using these features, developers can add new methods to classes, improve code readability, and maintain a cleaner code base. Understanding how to effectively use categories and extensions is essential for mastering Objective-C programming. Categories are a way to add methods to existing classes without the need for subclassing. This means you can extend classes like NSString or NSArray with additional functionality while keeping their original behavior intact. For example, you might create a category on NSString to add a method that reverses the characters in a string. Categories are declared in a header file with a specific syntax that includes the class name and a category name. This approach allows developers to share extensions across multiple files or projects, making it a flexible tool for adding utility methods. However, it is important to note that categories are typically used for adding methods rather than properties. One of the main advantages of using categories is that they eliminate the need to create subclasses for simple additions. This reduces code duplication and makes the code base easier to maintain. Categories also help in organizing methods into logical groups, which improves readability and makes it easier for other developers to understand the code. For instance, you could create a category on NSDate to add methods related to date formatting or calculations. Additionally, categories can sometimes be used to adopt protocols, allowing a class to conform to an interface without modifying its original implementation. This makes categories a valuable tool for extending functionality in a clean and efficient manner. Creating a category involves a specific syntax that begins with the @interface keyword, followed by the class name and the category name in parentheses. This declaration is placed in a header file where you define the methods that will be added to the class. The actual implementation of these methods is then written in a corresponding implementation file. For example, if you create a category on NSString called myCategory, you would declare the method in the header file and implement it in the M file. This separation of declarations and implementations ensures that the code remains organized and manageable. Categories are particularly useful when you want to add functionality that is not part of the original class, but is needed across multiple parts of an application. Let me demonstrate how to add a method to the NSString class using a category. In the header file, you would declare the method as part of the category, such as NSString reverse string. Then, in the implementation file, you would write the code to reverse the string. When this method is called, it behaves as if it were part of the original NSString class. For instance, you could invoke hello reverse string to get the reversed string alle. This example shows how categories allow you to extend system classes without modifying their original source code, which is especially useful when working with third-party libraries or frameworks. Extensions, on the other hand, are a special type of category that is used to declare private methods and properties. Unlike regular categories, extensions do not have a name and are typically declared in the implementation file of a class. This makes them ideal for hiding internal methods from other classes, which helps in encapsulating the implementation details of a class. Extensions are often used to add properties that are not intended for use outside the class. For example, you might use an extension to declare a private property that is used internally by the class, but not exposed to other parts of the application. This approach enhances the security and maintainability of the code. The key difference between categories and extensions lies in their purpose and usage. Categories are used to add methods to existing classes and are typically declared in header files. They can be used to extend both user-defined and system classes, making them a versatile tool for adding functionality. Extensions, however, are used for declaring private methods and properties and are usually found in implementation files. Unlike categories, extensions cannot add properties unless they are synthesized, which means they are more limited in their capabilities. Understanding these distinctions is crucial for deciding when to use each feature effectively. When working with categories and extensions, it is important to follow best practices to ensure clean and maintainable code. Categories should be used for adding shared functionality that can benefit multiple parts of the application. However, modifying system classes with categories should be done with caution, as it can lead to unexpected behavior. Extensions are best suited for declaring private methods and properties that are not intended for external use. Additionally, it is essential to choose unique names for categories to avoid conflicts, especially when working on large projects or integrating third-party libraries. By adhering to these guidelines, developers can maximize the benefits of categories and extensions while minimizing potential issues. In conclusion, categories and extensions are essential tools in Objective-C that allow developers to extend the functionality of classes in a flexible and efficient manner. Categories provide a way to add methods to existing classes without subclassing, making it easier to organize and reuse code. Extensions, on the other hand, help in hiding private implementation details, which improves code security and maintainability. Together, these features contribute to better code organization, reusability, and overall software design. By understanding and applying categories and extensions appropriately, developers can create more robust and scalable Objective-C applications. The singleton pattern is a design pattern that ensures a class has only one instance throughout the application's lifecycle. This single instance acts as a global access point, allowing any part of the code to retrieve it without needing to pass it around explicitly. It is particularly useful for managing shared resources such as configuration managers, database connections, or logging systems. By limiting the number of instances, the singleton pattern helps maintain consistency and avoids potential conflicts that could arise from multiple instances of the same class. For example, if multiple parts of an app try to initialize a database connection independently, the singleton ensures they all use the same connection, preventing resource exhaustion or data inconsistency. Using the singleton pattern offers several advantages. First, it provides centralized control over a single instance, making it easier to manage and modify the behavior of that instance in one place. This reduces coupling between classes because other parts of the code do not need to know the details of how the instance is created or maintained. Additionally, it simplifies resource management by ensuring that shared resources are accessed through a single point, which can improve efficiency. For instance, a singleton database manager can handle all queries and connections, preventing redundant or conflicting operations. This approach also makes it easier to enforce rules, such as ensuring that a resource is initialized only once and reused throughout the app. Implementing a singleton in Objective-C requires careful handling to ensure thread safety and proper initialization. The standard approach involves defining a class method, typically named shared instance, which returns the single instance of the class. To guarantee that the instance is created only once, even in a multi-threaded environment, we use the dispatchance function. This function ensures that the block of code inside it is executed exactly once, regardless of how many threads attempt to access it. For example, the static variable shared instance holds the instance, and the dispatchance block initializes it. This method avoids the pitfalls of traditional locking mechanisms like at synchronized, which can introduce performance overhead. The code demonstrates how to create a thread-safe singleton by leveraging Grand Central Dispatch, a core component of Apple's development ecosystem. Thread safety is a critical consideration when working with singletons, especially in applications that handle multiple threads. The dispatchance function is the preferred method for ensuring thread safety because it guarantees that the initialization code runs only once, even if multiple threads attempt to access the singleton simultaneously. Unlike at synchronized, which can lead to deadlocks or performance issues, dispatchance is optimized for this specific use case. It is essential to always access the singleton through its shared method to maintain this thread safety. Any direct access to the instance without going through the shared method could bypass the safeguards, leading to potential race conditions. This approach aligns with modern Objective-C best practices, which prioritize efficiency and reliability in concurrent environments. Memory management for singletons requires careful consideration to avoid unnecessary resource consumption. Since singletons are typically retained for the entire duration of the app's lifecycle, they are not released until the app terminates. This makes them suitable for objects that need to persist across the app's execution, such as a user session manager or a settings loader. However, overusing singletons for memory-intensive objects can lead to increased memory usage, which may impact performance. Developers should evaluate whether a singleton is the best fit for a particular task. For example, if an object is only needed in a specific part of the app, it might be better to create and release it as needed. Proper use of auto-release or retain depends on the memory management model being used, such as automatic reference counting arc or manual management. While the singleton pattern is powerful, it should be used judiciously. It is most appropriate for managing global state or shared resources that require a single point of control. However, overusing singletons can lead to tightly coupled code, making it harder to maintain and test. For instance, if a singleton accumulates too many responsibilities, it becomes a God object, which is difficult to modify or debug. In such cases, dependency injection is often a better alternative, as it allows for more flexible and testable code. By passing dependencies explicitly rather than relying on a global instance, developers can decouple components and make the code base more modular. This approach also facilitates unit testing, as dependencies can be mocked or replaced with test-specific implementations. There are several common pitfalls to avoid when using the singleton pattern. One is forcing a singleton where a simple object would suffice, which can introduce unnecessary complexity and reduce code clarity. For example, if a class only needs to be instantiated once, a singleton might be overkill, and a regular instance could be more straightforward. Another pitfall is incorrect thread safety implementation, such as relying on outdated methods like at synchronized instead of dispatchants. This can lead to race conditions or performance issues. Additionally, singletons can create dependencies that are hard to mock or test, making it difficult to write unit tests. To mitigate this, developers should consider alternative patterns, such as dependency injection, when testability is a priority. By being mindful of these issues, developers can leverage the singleton pattern effectively without compromising code quality. In summary, the singleton pattern is a valuable tool for managing shared resources and ensuring consistent behavior across an application. When implemented correctly, it provides thread safety, simplifies resource management, and reduces coupling between components. However, it is essential to use it judiciously and avoid over-reliance on it for tasks that do not require a single instance. By following best practices, such as using dispatchants for thread safety and considering dependency injection for testability, developers can maintain clean, scalable, and maintainable code. The singleton pattern, when applied thoughtfully, can enhance the structure of an Objective-C application while avoiding the common pitfalls associated with its misuse. UIKit is the fundamental framework that powers the user interface of iOS applications. It serves as the bridge between developers and the visual elements that users interact with daily. This framework includes a wide range of classes that handle everything from basic elements like buttons and labels to complex interactions like gesture recognition. By leveraging UIKit, Objective-C developers can craft applications that are not only visually appealing, but also highly functional. It manages the life cycle of an app, ensuring smooth transitions between different states, such as when the app is launched, suspended, or terminated. Understanding UI Kit is crucial for any developer aiming to build native iOS experiences. The UI Kit framework is composed of several key components that work together to create a cohesive user interface. Views form the foundation of any UI, with UI View acting as the base class for all visual elements. Subclasses like UI Label for text display and UI Button for user interaction are essential for building dynamic interfaces. View controllers play a critical role in managing these views, acting as the intermediary between the model data and the user interface. Controls such as sliders, switches, and text fields allow users to interact with the app, while layout tools like auto layout ensure that the UI adapts seamlessly to different screen sizes and orientations. Together, these components enable developers to create responsive and intuitive applications. At the heart of UI Kit's architecture lies the UI window, which acts as the container for all visible content in an app. This window is managed by the UI application instance, which coordinates the app's overall behavior. The UI View class serves as the base for all visual elements, providing a foundation for custom drawing and layout. View controllers are responsible for managing a group of views, handling user interactions, and coordinating with other parts of the app. The app delegate, on the other hand, oversees the app's lifecycle, responding to events such as app launch, background transitions, and termination. This structured approach ensures that the app remains organized and efficient. Several UI Kit classes are commonly used to build the visual components of an iOS application. The UI Image View class is designed to display images, making it ideal for incorporating graphics into the UI. Buttons, represented by UI Button, allow users to trigger actions through taps. Labels, created with UI Label, are used to present static text to the user. For user input, UI Text Field and UI Text View provide interfaces for entering text, whether it's a short phrase or a longer paragraph. These classes form the building blocks of any interactive iOS application, enabling developers to create rich and engaging experiences. Storyboards and XIBs are tools that simplify the process of designing user interfaces in Xcode. Storyboards allow developers to create a visual representation of an app's screens and their transitions, making it easier to plan the flow of the application. XIBs, on the other hand, are individual files that contain reusable UI components, which can be embedded into multiple parts of an app. Both storyboards and XIBs are designed using Interface Builder, a graphical tool within Xcode that enables drag and drop layout creation. These tools save time and reduce the need for writing extensive code for UI setup. Auto layout is a critical feature of UI Kit that ensures the user interface adapts to different screen sizes and orientations. Instead of relying on fixed positions, constraints define the relationships between views, such as their distance from the edges of the screen or their alignment with other elements. Common constraints include leading, trailing, top, and bottom anchors, as well as width and height specifications. By using auto layout, developers can create a single UI design that works across a variety of devices, from iPhones to iPads, without requiring separate layouts for each. Delegates and data sources are essential patterns in UI Kit that enable communication between different parts of an app. Delegates handle events and responses, such as when a user selects a row in a table view. Data sources provide the information that UI elements need to display, like the list of items in a table. These interactions are implemented through protocols in Objective-C, which define a set of methods that must be implemented by the class acting as the delegate or data source. This approach promotes modularity and makes it easier to manage complex user interfaces. Memory management in UI Kit is streamlined through automatic reference counting, which automatically tracks and releases objects when they are no longer needed. However, developers must be cautious to avoid retained cycles, which occur when two objects hold strong references to each other. To prevent this, delegates and other references should be declared as weak. Additionally, it is important to release resources such as images or animations when views are no longer visible, ensuring that the app uses memory efficiently and runs smoothly. Following best practices in UI Kit development can significantly improve the quality and maintainability of an app. The Model View Controller pattern helps organize code by separating data management, user interface logic, and control flow. Reusing UI components, such as custom views or buttons, reduces redundancy and speeds up development. Testing the UI on different device orientations and screen sizes ensures that the app provides a consistent experience across all devices. These practices not only enhance the user experience, but also make the code base easier to update and scale. In conclusion, UI Kit is an indispensable tool for developing iOS applications, offering a comprehensive set of classes and tools to create dynamic and responsive user interfaces. A deep understanding of its components and architecture allows developers to build applications that are both functional and visually appealing. By practicing with storyboards, mastering auto layout, and effectively using delegates and data sources, Objective-C developers can create high-quality iOS apps that meet the needs of modern users. Views are the fundamental components that form the user interface of any iOS application. They serve as the visual elements that users interact with, such as buttons that trigger actions, labels that display text, and images that convey information. These elements are all built using the UI View class, which acts as the base class for all visual components in UI Kit. By understanding how to create and manipulate views, developers can build dynamic and interactive applications that respond to user input and adapt to different screen sizes. This foundational knowledge is crucial for anyone looking to create polished, functional iOS apps. Creating views programmatically allows developers to build user interfaces directly through code, offering precise control over every aspect of the UI. For example, you can instantiate a UI View object and set its frame, background color, and other properties to define its appearance and behavior. The code UI View My View equals UI View alloc init with frame. CG rect make 0, 0, 100, 100 demonstrates how to create a view with specific dimensions. Once created, views must be added to the view hierarchy using the add subview method, which ensures they are displayed on the screen. This approach is particularly useful for dynamic interfaces where elements may change based on user actions or data updates. Interface Builder provides a visual way to design user interfaces using Xcode storyboard or XIB files. Instead of writing code, developers can drag and drop UI elements like buttons and labels onto a canvas, making it easier to visualize the layout. These elements can then be connected to code through outlets and actions, allowing developers to manipulate their properties and respond to user interactions. This method is ideal for rapid prototyping and offers a more intuitive approach to designing complex interfaces. However, it's important to balance visual design with code to maintain flexibility and scalability. The structure of views in iOS is organized in a hierarchical manner, where each view can have a parent view and multiple subviews. This parent-child relationship is navigated using properties like superview and subviews, which allow developers to access and manage the hierarchy. To ensure views are positioned and sized correctly across different devices, it's essential to use auto layout. This system defines constraints that dynamically adjust view positions and sizes based on the screen's dimensions. By avoiding hard-coded frames, developers can create responsive designs that work seamlessly on various iPhone and iPad models. The life cycle of a view involves several key methods that dictate when and how views are loaded, displayed, and released. The viewDidLoad method is called once when the view is first loaded, making it suitable for initializing components. The viewWillAppear and viewDidAppear methods are used to prepare and update the view before it becomes visible. It's important to avoid performing resource-intensive tasks in viewDidLoad to maintain smooth performance. When a view is no longer needed, resources should be released in viewDidDisappear or dealloc. Though automatic reference counting arc simplifies this process by handling memory management automatically. Adding and removing subviews is a common task in iOS development, requiring careful management to maintain a clean and efficient view hierarchy. The Add Subview method is used to attach a view to its parent, while Insert Subview at Index allows for precise placement within the hierarchy. When a view is no longer needed, it should be removed using Remove from Superview or Remove Subview to prevent memory leaks. The Subviews property provides a way to inspect all child views of a given view, which is useful for debugging or dynamically modifying the UI. Properly managing these operations ensures that the application remains responsive and avoids unnecessary resource consumption. User interaction is a critical aspect of any iOS app, and views must be configured to respond to touch events and gestures. By default, views are not interactive, so the user interaction-enabled property must be set to yes to enable this functionality. Developers can use gesture recognizers like UI Tap Gesture Recognizer or UI Pan Gesture Recognizer to detect specific actions such as taps or swipes. For buttons and controls, the target action pattern is used to link user actions to specific methods. For more granular control, developers can override touch event methods like touches began, touches moved, and touches ended to handle custom interactions. Best practices for view management ensure that applications are maintainable, efficient, and scalable. Using auto layout is essential for creating adaptive interfaces that work across different screen sizes and orientations. Overloading a single view with too many subviews can lead to performance issues, so it's better to organize views into reusable components. Reusing views, such as table view cells, helps optimize memory usage and improve app performance. Separating view logic from business logic keeps the code base clean and easier to manage, allowing developers to focus on specific responsibilities without unnecessary complexity. In conclusion, views are the cornerstone of iOS app development, serving as the bridge between users and the underlying functionality of an application. Whether creating views programmatically or using Interface Builder, developers must prioritize flexibility and efficiency in their designs. By mastering layout techniques like auto layout and adhering to best practices, developers can build robust, scalable applications. Applying these principles ensures that the code remains clean, maintainable, and capable of adapting to future changes in user needs and device capabilities. View controllers are fundamental components in iOS development that manage the views, user interactions, and data within an application. They serve as the critical link between the user interface and the underlying data model, ensuring seamless communication between the two. Their primary responsibilities include loading views into memory, handling user events such as taps or gestures, and coordinating with other parts of the app like data storage or network services. By centralizing these tasks, view controllers help maintain a structured and organized code base, making it easier to manage complex user interfaces and interactions. There are several types of view controllers in iOS, each designed for specific use cases. The base class UI View Controller is used to manage a single view and is the foundation for all other view controllers. UI Navigation Controller is a container view controller that allows users to navigate through a stack of view controllers, providing a back button and a navigation bar for hierarchical navigation. UI Tab Bar Controller offers a tab-based interface, enabling users to switch between different sections of an app. Finally, UI Split View Controller is tailored for iPad apps, displaying two view controllers side by side to maximize screen space and enhance multitasking. Navigation in iOS applications often involves moving between view controllers using a stack-based approach. When a user navigates to a new screen, the view controller is pushed onto the stack, and when they return, it is popped off. This stack structure ensures a clear and predictable navigation flow. Navigation bars and toolbars play a vital role in this process, providing a consistent interface for actions like back navigation, title display, and custom buttons. These elements help users understand their current location within the app and make it easier to traverse between screens. The UI Navigation Controller is a powerful container view controller that manages a stack of view controllers, allowing for smooth, hierarchical navigation. It provides a navigation bar at the top of the screen, which displays the title of the current view controller and includes a back button to return to the previous screen. Developers can interact with the navigation stack using methods like Push View Controller Animated. To add a new view controller and Pop View Controller Animated to remove the current one. This structure is essential for apps with deep navigation paths, such as settings menus or multi-step forms. Segues are transitions between view controllers that are triggered by user actions, such as tapping a button or selecting a table view cell. There are several types of segues, including Show, which pushes a new view controller onto the navigation stack, Modal, which presents a view controller in a full screen overlay, Custom, which allows for custom animations, and Unwind, which navigates back to a previous view controller. Segues can be configured directly in the storyboard or programmatically using the Perform Segueth Identifier Sender method, offering flexibility in how navigation is implemented. Creating custom navigation transitions involves subclassing UI storyboard segue and defining the animation logic in the Perform method. This allows developers to design unique transitions that enhance the user experience, such as sliding, fading, or rotating effects. By setting the segues class in the storyboard, developers can control how the transition is executed. Custom segues are particularly useful for apps that require a distinctive visual style, or for implementing complex navigation patterns that go beyond the default options. To maintain clean and scalable code, it is essential to follow best practices when working with view controllers. Each view controller should focus on a single responsibility, avoiding the accumulation of unrelated logic. Business logic should be delegated to helper classes or models, keeping the view controller lightweight. Communication between view controllers can be efficiently managed using delegation and protocols, which allow for loose coupling and easier maintenance. By adhering to these principles, developers can create more modular and readable code that is easier to update and debug. In summary, view controllers are the backbone of iOS app architecture, enabling the management of user interfaces and navigation flows. Mastering navigation controllers and segues allows developers to create complex and intuitive app experiences. By following best practices, such as maintaining single responsibilities and using delegation, developers can ensure their code remains clean, scalable, and easy to maintain. Understanding these concepts is crucial for building robust and user-friendly iOS applications. Auto layout is a powerful system designed to dynamically position and size user interface elements. This approach ensures that your application's layout remains consistent and visually appealing across a wide range of screen sizes and orientations. Unlike traditional frame-based layouts, which rely on fixed coordinates, auto layout uses constraints to define the relationships between different UI components. These constraints act as rules that dictate how elements should be positioned and sized relative to each other or to the screen. By replacing older methods, auto layout provides greater flexibility, making it easier to create responsive designs that adapt to different devices and user interactions. This is particularly important in modern app development, where users access applications on everything from small smartphones to large tablets. Constraints are the foundation of auto layout, serving as the rules that govern the positioning, size, and alignment of user interface elements. Each constraint includes a constant, which is a fixed value, such as 20 or 100. These constants help define specific measurements or offsets. The relations in constraints determine how elements interact, such as being equal to, greater than, or less than another element. For example, a constraint might specify that one view's leading edge is equal to another view's trailing edge. Additionally, priority levels assign importance to constraints, distinguishing between required and optional rules. This allows the system to handle conflicts by prioritizing the most critical constraints, ensuring that the layout remains functional even in complex scenarios. In code, constraints are created using the NS Layout constraint class, which provides a structured way to define relationships between UI elements. For instance, you can create a constraint that sets the leading edge of one view equal to the trailing edge of another view, with a multiplier of 1 and a constant of 10. This line of code establishes a precise relationship between the two views. Once defined, these constraints must be added to the view hierarchy using methods like addConstraint or addConstraints. This process integrates the constraints into the layout system, allowing the auto layout engine to calculate the correct positions and sizes during runtime. By coding constraints directly, developers gain fine-grained control over the layout, which is especially useful for complex or dynamic interfaces. There are several common types of constraints that developers use to build flexible layouts. Leading and trailing constraints position elements relative to the edges of the screen, making them ideal for aligning elements to the left or right. Top and bottom constraints handle vertical alignment, ensuring elements are properly spaced from the top or bottom of their container. Width and height constraints define the size of elements, either as fixed values or proportional to other elements. Finally, centering constraints align elements horizontally or vertically within their container, creating balanced and aesthetically pleasing layouts. By combining these constraint types, developers can create responsive designs that adapt to different screen sizes and orientations. Once constraints are defined, they must be activated to take effect in the layout. This is typically done using the Activate Constraints method or the newer Activate method, which simplifies the process by allowing multiple constraints to be activated at once. For example, you can pass an array of constraints to activate, ensuring they are all applied simultaneously. Activating constraints is crucial because it tells the auto layout system to start using them when calculating the layout. Conversely, if constraints need to be removed or modified, they can be deactivated using deactivate constraints. This flexibility allows developers to dynamically adjust layouts based on user interactions or changing application states. Debugging layout issues can be challenging, but Xcode provides a powerful tool called Debug View Hierarchy to help visualize the layout. This tool allows developers to inspect the structure of views and identify potential problems. Common issues include conflicting constraints, where two or more rules contradict each other, and uninstalled constraints, which may be missing from the view hierarchy. By examining these conflicts, developers can adjust their constraints to resolve inconsistencies. Another useful technique is enabling the auto-resizing mask, which provides a quick way to test layout changes during development. However, it is important to note that this is a temporary solution and should be replaced with proper constraints for production-ready designs. To create robust and maintainable layouts, it is essential to follow best practices when working with auto layout. Prioritizing constraints helps avoid ambiguity by ensuring that critical rules take precedence over less important ones. Hard-coding frame values should be avoided, as it limits the flexibility of the layout. Instead, relying on constraints allows the interface to adapt to different screen sizes and orientations. Using IB outlet connections for views simplifies constraint management by providing direct access to elements in code. Finally, testing layouts on multiple device sizes and orientations is crucial to ensure that the application looks and functions correctly across all platforms. These practices not only improve the user experience, but also make the development process more efficient. Auto layout is an essential tool for creating adaptive user interfaces in Objective-C by defining dynamic relationships between UI elements. Constraints ensure that layouts remain consistent and functional across different devices. This approach is vital for modern app development, where users expect seamless experiences on a variety of screen sizes and orientations. Mastering auto layout allows developers to build scalable and flexible interfaces that enhance usability and reduce the need for manual adjustments. As a result, Understanding and effectively using constraints is a critical skill for any Objective-C developer aiming to create high-quality, responsive applications. File handling is a fundamental aspect of software development that allows applications to read, write, and manage data stored in files. This capability is essential for ensuring that data remains accessible even after an app is closed or a device is restarted. In iOS and macOS environments, Objective-C provides a robust set of tools to handle file operations efficiently. Classes like NS File Manager, NS Data, and NS Coder are central to these tasks, enabling developers to interact with the file system, manipulate binary data, and serialize objects. Key concepts include understanding file paths, which are the addresses where files are stored, and differentiating between file types such as text files, which contain human-readable data, and binary files, which store data in a format optimized for machines. Managing directories is also crucial, as it helps organize files and ensures that data is stored and retrieved systematically. To interact with the file system in Objective-C, developers rely on the NS File Manager class, which acts as a gateway to perform various operations. Common tasks include creating new files, deleting existing ones, moving or copying files between locations, and checking for the existence of files. Retrieving file paths is a critical step in these operations, and the NS search path for directories in domains function helps locate standard directories like the user's documents or caches. For example, this function can return the path to the app's sandbox directory, ensuring that files are stored in the correct location. Additionally, developers can check if a file exists using the fileExistsAtPath method, which returns a Boolean value. To gather more details about a file, such as its size or modification date, the attributeSatPath method provides access to metadata. These tools collectively empower developers to manage files with precision and control. Reading and writing files in Objective-C involves different approaches depending on the file type. For text files, the NSString class offers methods like initWithContentsOfFile, encoding error, to load data from a file, allowing developers to specify the encoding format, such as UTF-8. Similarly, the write-to-file atomically encoding error method enables writing text data to a file, with the atomically parameter ensuring that the right operation is either fully completed or not at all, preventing data corruption. For binary data, which is often used for images, audio, or custom formats, the NS data class is indispensable. Methods like write to file atomically and data with contensive file facilitate reading and writing binary data efficiently. However, these operations can fail due to various reasons, such as invalid file paths or insufficient permissions. To handle such scenarios, developers use NS error pointers to capture and respond to errors, ensuring that the app remains stable and user-friendly. When it comes to data persistence, Objective-C offers several options tailored to different needs. File-based storage, such as using property lists plists or custom formats, is ideal for simple data structures. Plists, for instance, allow storing data in XML or binary format using NS dictionary or NS array, making them suitable for small to medium-sized datasets. For more complex scenarios, Core Data provides a powerful framework for managing object graphs and relational data, often backed by a SQLite database. This approach is particularly useful for applications requiring advanced querying, relationships, and scalability. Additionally, the Keychain Services API is designed for securely storing sensitive information like passwords or encryption keys, protecting it from unauthorized access. Choosing the right method depends on factors such as the complexity of the data, the need for security, and the performance requirements of the application. Property lists or plists are a straightforward way to store data in Objective-C, offering both XML and binary formats. These files are structured using NS dictionary or NS array, making it easy to store and retrieve basic data types like strings, numbers, arrays, and dictionaries. For example, a plist can store user preferences or configuration settings, which can be saved using the write to file atomically method and loaded back with dictionary with contents of file. However, plists are limited in their ability to handle complex objects or deep hierarchies, as they can only store primitive types and simple collections. This makes them unsuitable for scenarios involving custom classes or large datasets. Despite these limitations, plists remain a popular choice for their simplicity and ease of use, especially in smaller applications or when quick data storage is required. Archiving with NS Coder is a powerful technique for serializing objects in Objective-C, allowing developers to save complex data structures to files and restore them later. The NS-keyed archiver class is used to convert objects into a format that can be written to a file, while NS-keyed unarchiver is used to reverse the process. To enable this, custom classes must conform to the NS coding protocol, which requires implementing two methods: encode with coder, to specify how the object's properties are encoded, and init with coder, to reconstruct the object from the encoded data. This approach is particularly useful for saving and restoring object graphs, such as a user's entire application state, without manually converting each object to a file. Archiving is ideal for scenarios where data needs to be persisted in a structured and reusable manner, making it a preferred choice for applications with intricate data models. Core data is a comprehensive framework designed to manage the model layer of an application, providing tools for object persistence, relationships, and querying. At its core data uses managed objects to represent data, which are organized within managed object contexts. These contexts act as a scratch pad for changes, which are then saved to a persistent store, such as a SQLite database. This architecture allows for efficient data management with features like faulting, which delays the loading of data until it is needed, and change tracking, which monitors modifications to objects. Core data also supports complex queries, making it suitable for applications with large, structured datasets. By abstracting the underlying storage details, core data enables developers to focus on the business logic of their applications while ensuring scalability and performance. Adhering to best practices in file handling is crucial for building reliable and efficient applications. Error handling should be a priority, as file operations can fail due to various reasons, such as invalid paths or insufficient permissions. Developers should always validate file paths and check for errors using NS error pointers to provide meaningful feedback to users. For large files or operations that might block the main thread, it is advisable to perform these tasks on background threads using Grand Central Dispatch or NS Operation Queue. Sensitive data, such as user credentials, should be protected using encryption or the Keychain Services API to prevent unauthorized access. Additionally, developers must ensure that resources like file handles are properly closed and memory is managed to avoid leaks, optimizing data serialization techniques, such as using efficient encoding formats, can further enhance performance and reduce resource consumption. In conclusion, file handling and data persistence are essential components of any application, enabling data to be stored, retrieved, and managed effectively. Objective-C provides a rich set of tools, including NS File Manager for basic file operations, NS Coder for object archiving, lists for simple data storage, and core data for complex data models. Each method has its strengths and is suited to different scenarios, so choosing the right approach depends on factors like data complexity, security requirements, and performance needs. By following best practices such as error handling, background processing, and secure storage, developers can ensure their applications are robust, scalable, and user-friendly. Mastering these concepts allows for the creation of applications that not only function well, but also provide a seamless experience for users. Strings in Objective-C are represented by the NS string and NS mutable string classes. These classes provide the foundation for working with text in applications. NS string is immutable, meaning once a string is created, its contents cannot be changed. This immutability ensures that the string remains constant throughout its life cycle, which can be beneficial for performance and thread safety. NS mutable string, on the other hand, allows for modifications such as appending, inserting, or deleting characters. Common operations include creating strings, combining them through concatenation, comparing their contents, and formatting them for display. Whether you are handling user input, processing data, or generating output, strings are essential for managing text data in applications. Understanding these classes is crucial for any Objective-C developer. To create and initialize strings in Objective-C, you can use methods like initWithString or stringWithFormat. For example, you can directly assign a string using the literal syntax NS string greeting equals @hello world. This is a concise and efficient way to create strings. For NS mutable string, you need to use initWithCapacity or stringWithFormat to allocate memory for the string. Specifying a capacity helps optimize memory usage by reserving space for future modifications. Additionally, strings can be created from external sources such as files, URLs, or user input. For instance, You might read a string from a file using data with contents of file, or capture user input from a text field. These methods provide flexibility for handling dynamic or external data sources. String manipulation techniques in Objective-C include concatenation, extraction, comparison, and formatting. To concatenate strings, you can use the string by appending string method, which appends one string to another. For example, string by appending string at creates a new string with an exclamation mark. Extracting parts of a string is possible with substring with range, which takes a range of characters. This is similar to slicing in other programming languages. Comparing strings can be done using compare. For ordered comparisons, or is equal to string, to check for exact matches. Formatting methods like uppercase string, lowercase string, and capitalized string allow you to transform the case of characters. These tools are invaluable for tasks such as processing user input, generating reports, or preparing data for display. Mastery of these techniques enhances your ability to work with text efficiently. NSData is a class used to represent raw binary data in Objective-C, unlike strings, which handle text. NSData is designed for non-text data, such as images, files, or network responses. It acts as a container for a sequence of bytes, making it ideal for scenarios where you need to work with unstructured data. For example, you might use NSData to store a JPEG image or a binary file. NSData itself is immutable, meaning its contents cannot be changed after creation. If modifications are required, you should use NS mutable data, which provides methods for appending, inserting, or modifying data. This distinction is important for managing data efficiently, especially when dealing with large or complex data sets. Converting strings to NSData in Objective-C is straightforward using the data using encoding method. For example, NSData data equals string data using encoding, NSUTF-8 string encoding, converts an NS string into a binary representation. The encoding parameter specifies how the characters are represented in bytes, such as UTF-8, ASCII, or other standards. Choosing the correct encoding is critical to ensure data integrity, as mismatched encodings can lead to corrupted or unreadable data. For instance, UTF-8 is widely used because it supports all Unicode characters and is backward compatible with ASCII. When converting, you can also handle encoding errors by using options like NSUTF 8-string encoding or NSASCII string encoding, which define how invalid sequences are processed. This step is essential for applications that rely on precise data conversion. To convert NS data back into a string, you can use the initwith data encoding initializer. For example, NS string string equals NS string alloc initwith data encoding NSUTF 8-string encoding reconstructs the original text from binary data. The encoding must match the one used during conversion to avoid corruption. If the data is invalid or the encoding is incorrect, the result will be nil. So it's important to check for this condition. This process is commonly used when reading files, receiving network data, or retrieving information from a database. Ensuring that the encoding is consistent is vital for preserving the accuracy of the data. Developers should always validate the result of such conversions to handle unexpected scenarios gracefully. NS data has numerous practical applications in Objective-C development. For instance, you can read files into NS data using data with contents of file, and then process or display the contents. When working with networks, NS data is used to send and receive data through NSERL session, allowing you to handle responses from web servers. Storing binary data in core data or user defaults is another common use case, though the latter is typically reserved for small amounts of data. Additionally, NS data is essential for working with images, audio, or video files, as these formats are inherently binary. By leveraging NS data, developers can handle complex data types and integrate them seamlessly into their applications, whether for local storage, transmission, or manipulation. In summary, strings represented by NS string and NS mutable string are fundamental for handling text in Objective-C. They provide the tools to create, modify, and compare textual data efficiently. NS data, on the other hand, is critical for working with binary data, enabling the storage and manipulation of non-textual information. Proper encoding and decoding practices ensure that data remains intact during conversions between strings and binary formats. By combining these classes, developers can build robust applications that process and manage diverse data types. Whether you are building a simple app or a complex system, understanding these concepts is essential for effective Objective-C programming. NSERL session is the primary API for network communication in Objective-C. It has become the standard tool for developers working on iOS and macOS applications. Unlike the older NSERL connection, which is now deprecated, NSERL Session offers a more modern and flexible approach to handling network tasks. It supports three main types of tasks: data tasks for fetching information, download tasks for retrieving files, and upload tasks for sending data to servers. Additionally, NSERL Session provides the ability to execute tasks in the background, even when the app is not actively running. This makes it ideal for scenarios like downloading large files or uploading data without interrupting the user experience. The API also offers two main ways to handle task completion delegation, which allows for more control and customization, and completion handlers, which are simpler and more straightforward for basic operations. To create an NSERL session, you start by defining its behavior using NSERL session configuration. This configuration acts as a blueprint for how the session will operate. There are three primary configuration types. The default configuration is the most commonly used and leverages shared cache and credential storage, making it efficient for typical network requests. The ephemeral configuration is designed for scenarios where privacy is critical, such as private browsing, as it does not persist any data to disk. The background configuration, on the other hand, allows tasks to continue running even if the app is suspended or terminated, which is particularly useful for long-running operations. Once you have chosen a configuration, you create the session by initializing an NSERL session object with that configuration. This setup ensures that your network interactions are tailored to the specific needs of your application. NSERL session supports three main types of tasks, each suited for different use cases. Data tasks are used to fetch data from a URL, such as retrieving JSON or XML content from an API. These tasks are initiated using the data task with completion handler method, which provides the received data and any errors. Download tasks are designed for downloading files, such as images or documents, and they store the data in a temporary location on the device. This is useful for handling large files that may not fit in memory. Upload tasks, meanwhile, are used to send data to a server, such as when submitting a form or uploading a file. They are created using the upload task with from completion handler method, which allows you to specify the data to be sent. Each task type is optimized for its specific purpose, making Enserl Session a versatile tool for handling various network operations. Handling responses in Enserl Session involves using delegate methods to monitor the life cycle of network tasks. One key method is URL Session did receive completion handler, which is called when a response is received from the server. This allows you to inspect the response headers and decide how to proceed, such as accepting or rejecting the response. Another important method is URL Session did finish collecting, which provides metrics about the task, like the number of bytes transferred or the duration of the request. Once the response data is available, you can parse it using tools like NSJSON serialization for structured data or NSXML parser for XML content. It's also crucial to check for errors, which can be done in the URL Session did fail with error method. This ensures that your app can handle unexpected issues gracefully, such as network timeouts or server errors, and provide meaningful feedback to the user. Error handling is a critical aspect of network programming, and Enserl Session provides robust mechanisms for this. NS error objects contain detailed information about failures, including error codes and descriptions. These errors can occur at various stages, such as when a URL is invalid, the network connection is lost, or the server returns an error. Developers should handle these errors within completion handlers or delegate methods to ensure the app remains responsive and stable. For example, if a URL is malformed, the app can prompt the user to check the input. If a server error occurs, the app might retry the request or display a message. The user info dictionary of an NS error often contains additional context, such as the specific HTTP status code or the original request that caused the error. By leveraging these details, developers can create more resilient and user-friendly applications. Background transfers are a powerful feature of Enserl Session that enable tasks to continue running even when the app is not in the foreground. This is particularly useful for applications that need to download or upload large files without requiring the user to keep the app active. To use background tasks, you must create a session with a unique identifier, which allows the system to manage the task independently of the app. When the app is launched again, the delegate methods can be used to resume or complete the task. However, it's important to handle temporary files properly, as they are stored in a specific directory and may need to be cleaned up after the task is complete. This ensures that the device's storage remains efficient and that sensitive data is not left exposed. Background execution also requires careful management of system resources to avoid unnecessary battery drain or performance issues. Authentication and security are essential considerations when working with network requests. nSurl session provides methods to handle HTTP authentication, such as when a server requires a username and password. The URL session did receive completion handler. Delegate method is used to prompt the user for credentials or to automatically provide stored credentials using nSurl credential. This helps streamline the authentication process and improves the user experience. For secure connections, it's important to enable SSL TLS validation to prevent man-in-the-middle attacks. nSurl session automatically validates server certificates, but developers should also verify that the server's domain matches the expected value. By combining proper authentication mechanisms with secure communication protocols, applications can protect user data and maintain trust. Following best practices when using nSurl session ensures that your network code is reliable, efficient, and maintainable. Always validate URLs before making requests to avoid errors caused by malformed or incorrect addresses. Handling network state changes, such as switching between Wi-Fi and cellular data, can help your app adapt to different environments. For simple tasks, completion handlers are ideal due to their simplicity, while delegates offer more control for complex workflows. It's crucial to avoid blocking the main thread during network operations, as this can lead to a poor user experience. Instead, perform these tasks on background threads and update the UI once the operation is complete. Testing your app under various network conditions, such as slow or unstable connections, helps identify potential issues and ensures robust performance. By adhering to these practices, developers can create applications that are both functional and user-friendly. nSurl session is a fundamental tool for modern network communication in Objective-C, offering a flexible and powerful way to handle data, downloads, and uploads. Mastering its features, such as task types, error handling, and background execution is essential for building efficient and reliable applications. Applying best practices ensures that your code is not only functional, but also optimized for performance and user experience. Real-world scenarios, such as making API calls or handling file downloads, provide valuable opportunities to practice and refine your skills. By understanding and utilizing N-Searle session effectively, developers can create applications that meet the demands of today's connected world. JSON and XML are two of the most common data formats used for exchanging information between systems. JSON, which stands for JavaScript Object Notation, is known for being lightweight and easy to read. It uses a simple structure of key-value pairs, making it ideal for modern web APIs where speed and efficiency are crucial. XML, or Extensible Markup Language, is more structured and allows for complex data hierarchies. It uses tags and attributes to define data, which makes it highly flexible, but also more verbose. Both formats play a vital role in data serialization, allowing Objective-C applications to communicate with servers, store data, and integrate with other systems. Understanding their strengths and use cases is essential for any developer working with data in Objective-C. The structure of JSON and XML differs significantly. JSON relies on key-value pairs and can include nested objects and arrays, creating a flat and straightforward hierarchy. For example, a JSON object might look like name, John, age 30, where each key is associated with a value. XML, on the other hand, uses a tag-based system where elements are enclosed in start and end tags. A similar example in XML would be person name, John/name, age 30/age/person, where each element is explicitly defined. JSON is generally easier to parse and requires less code, making it faster for simple data exchanges. XML, however, offers greater flexibility for complex data structures, such as those found in legacy systems, or when precise control over data formatting is necessary. Parsing JSON in Objective-C is typically done using the NSJSON serialization class. This class provides methods to convert JSON data into Objective-C objects like NSDictionary or NSArray. The process begins by ensuring the JSON data is properly encoded, often using UTF-8 encoding. Once the data is ready, you can use the JSON object with data method, which takes the data and returns a dictionary or array. It's crucial to handle errors during parsing, as invalid JSON can cause crashes. By using an NS error pointer, you can catch and respond to issues like malformed syntax or unexpected data types. This error handling ensures your application remains stable even when dealing with unreliable data sources. Parsing XML in Objective-C requires the use of the NSXML parser class, which processes XML documents incrementally. This approach is beneficial for large files, as it avoids loading the entire document into memory at once. To implement XML parsing, you need to set up a delegate object and implement specific delegate methods. The parser didStartElement method is called when an element starts, allowing you to track the current node. The parser foundCharacters method captures the text content between tags, and the parser didEndElement method signals when an element ends. By carefully managing these methods, you can build a data model that accurately reflects the structure of the XML document. This step-by-step process ensures that even deeply nested XML structures are handled correctly. Here's an example of how to parse JSON in Objective-C. You start by creating an NS error object to capture any errors during the process. Then, you use the JSON object with data method, passing in the JSON data and a set of options. The options parameter can be set to 0 if you don't need any special parsing behavior. This method returns an NS dictionary or NS array, which you can then use in your application. For XML, the process involves initializing an NSXML parser with the XML data and setting its delegate to self. Once the parser is configured, calling the parse method initiates the parsing process. Both methods require robust error handling and data validation to ensure the parsed data is reliable and safe to use. When working with JSON and XML parsing, following best practices is essential. First, always validate the data before attempting to parse it. This helps prevent crashes caused by malformed or unexpected input. For large datasets, consider using asynchronous parsing to avoid freezing the user interface. Handling nested structures requires careful attention, as missteps can lead to incorrect data models or memory issues. In general, prefer JSON for modern applications and APIs due to its simplicity and speed, while using XML for legacy systems or scenarios where complex data structures are necessary. By adhering to these practices, you can ensure your applications handle data efficiently and reliably. In conclusion, JSON and XML are fundamental tools for data exchange in Objective-C. Their unique strengths make them suitable for different scenarios, from lightweight web APIs to complex legacy systems. Choosing the right format depends on your project's requirements, such as performance needs or existing infrastructure. Mastering parsing techniques allows you to handle data effectively, improving the functionality and stability of your applications. Practicing with real-world examples helps reinforce these concepts, making you more proficient in using these formats in actual development workflows. By understanding and applying these principles, you can build more robust and efficient Objective-C applications. Debugging and profiling are essential components of the development process. When working with Objective-C, these practices help ensure that your code is not only functional, but also efficient and reliable. In Objective-C, where memory management and object interactions are critical, debugging becomes a lifeline for identifying and resolving issues that may not be immediately obvious. Xcode, the primary development environment for Apple platforms, offers a robust set of tools to assist with both debugging and profiling. These tools allow developers to analyze their code in real time, track down errors, and optimize performance. By the end of this session, you will gain the skills to effectively identify and resolve bugs, as well as enhance the overall performance of your applications. The Xcode debugger, which is based on the LLDB engine, is one of the most powerful tools available for runtime analysis in Objective-C. LLDB provides a command line interface and a graphical user interface within Xcode, making it accessible for developers of all skill levels. Key features of the debugger include setting breakpoints, which allow you to pause code execution at specific lines to inspect the state of your program. Step-through execution enables you to navigate through your code line by line, observing how variables and objects change over time. Additionally, the debugger allows you to inspect variables, view their values, and examine the call stack to understand the flow of execution. The Debug Navigator in Xcode serves as a central hub for monitoring threads, memory usage, and the overall execution flow of your application, providing critical insights during the debugging process. Effective debugging in Objective-C often relies on a combination of techniques to pinpoint and resolve issues. One of the most fundamental methods is setting breakpoints, which allow you to pause execution at specific lines of code to examine the program's state. This is particularly useful when trying to understand the behavior of complex logic, or when tracking down elusive bugs. Another common approach is using NSLog, or the print function, to output real-time information about variables and program flow. While these statements are simple, they can provide invaluable insights during development. The debugger console also allows you to inspect variables and view stack traces, which help trace the sequence of function calls leading to a particular point in the code. Conditional breakpoints add another layer of precision, enabling you to pause execution only when specific conditions are met, which is especially helpful when dealing with loops or repetitive tasks. Instruments is a comprehensive suite of profiling tools integrated into Xcode, designed to analyze the performance of your Objective-C applications. Unlike the debugger, which focuses on runtime analysis, Instruments provides a deeper look into how your app interacts with system resources. This toolset is invaluable for identifying performance bottlenecks, memory issues, and other critical problems that may affect user experience. Instruments works seamlessly with Xcode, allowing you to launch it directly from the development environment. It includes a variety of instruments tailored to specific aspects of app performance, such as memory usage, CPU activity, and energy consumption. By leveraging these tools, developers can gain a detailed understanding of how their applications behave under different conditions and optimize them accordingly. When it comes to memory profiling in Objective-C, the leaks instrument is a critical tool for detecting memory leaks, which occur when objects are not properly released and continue to consume memory. Memory leaks can lead to excessive memory usage and, in severe cases, cause an application to crash. The allocations instrument provides a detailed view of how objects are allocated and deallocated over time, helping you track the life cycle of objects and identify potential issues. Retain cycles, where two or more objects hold strong references to each other, are a common source of memory leaks in Objective-C by using instruments. You can monitor these patterns and ensure that your code follows proper memory management practices, such as using weak references where appropriate. This is especially important in applications that handle large datasets or complex object graphs. Performance profiling in Objective-C relies on tools like the Time Profiler, which helps identify CPU bottlenecks by analyzing how much time is spent in specific functions or methods. This is crucial for optimizing the efficiency of your code, especially in performance-critical sections such as animations or data processing. The Energy Diagnostics instrument provides insights into how your app consumes battery power, highlighting areas where it may be using excessive energy, such as through frequent background activity or inefficient code. For applications that rely heavily on graphical elements, the Core Animation instrument is invaluable for diagnosing rendering performance issues. It can reveal problems such as dropped frames or excessive CPU usage during animations, allowing you to fine-tune your code for smoother user experiences. Adopting best practices for debugging can significantly improve your efficiency and the quality of your code. A key principle is to reproduce issues consistently before attempting to debug them. This ensures that you can reliably test your fixes and verify that the problem is resolved. Using version control systems like Git allows you to track changes and isolate the specific code modifications that introduced a bug, making it easier to roll back or fix the issue. Combining NS-log statements with breakpoints provides a powerful approach to troubleshooting, as it allows you to gather real-time data while also inspecting the program's state. Finally, testing your application on a variety of devices and iOS versions helps uncover compatibility issues that may not be apparent during development. This ensures that your app performs well across different hardware and software configurations. Debugging and profiling are indispensable skills for any Objective-C developer, as they directly impact the stability, performance, and user experience of your applications. Xcode's debugger and instrument offer a wealth of features to help you identify and resolve issues efficiently. By mastering these tools and applying best practices, you can ensure that your code is not only functional, but also optimized for performance and reliability. As you continue to develop in Objective-C. Remember that consistent debugging and profiling are ongoing processes that contribute to the long-term success of your projects. Unit testing is a critical practice in software development that involves verifying the correctness of individual components of a program. By testing each function or method in isolation, developers can ensure that these building blocks behave as intended, which is essential for creating robust applications. This approach not only enhances the reliability of the code base, but also makes it easier to maintain over time. When issues arise, unit tests act as a safety net, allowing developers to identify and fix bugs early in the development cycle. Additionally, unit testing supports refactoring by providing confidence that changes to the code base do not introduce new errors. This practice ultimately leads to more stable and scalable software. XC-Test is the official unit testing framework provided by Apple for developers working with Objective-C. It offers a comprehensive set of tools that enable programmers to write, organize, and execute tests efficiently. This framework is deeply integrated into Xcode, the primary development environment for Apple platforms, making it seamless to run and debug tests directly within the IDE. XC-Test supports features like test discovery, which automatically identifies test methods in the code, and test execution, allowing developers to run tests in bulk or individually. Its design encourages a structured approach to testing, ensuring that all aspects of an application can be validated systematically. To begin writing tests for an Objective-C project, the first step is to create a test target in Xcode. This can be done by navigating to the File menu and selecting New followed by Target. When adding a new target, developers should choose the Unit Testing Bundle option, which is specifically designed for testing Objective-C code. Once the test target is created, it must be linked to the main project to ensure it can access the necessary source files. Finally, the test target needs to import the header files of the main project, allowing the tests to interact with the code under test. This setup provides a clean separation between the application code and its corresponding tests. Writing test cases in XC-Test involves creating classes that subclass the XC-Test case class. This subclassing establishes a foundation for organizing tests around specific functionalities. Each test class typically includes a setup method, which is used to initialize any shared resources or data before each test runs, and a tear-down method, which cleans up those resources after the test completes. Test methods themselves must follow a specific naming convention, starting with the word test to indicate their purpose. For example, a method named test addition would verify the correctness of an addition function. This structure ensures that tests are easy to identify and manage within the project. XCTest provides a variety of assertion macros to evaluate conditions during testing. These macros allow developers to check for expected outcomes and trigger failures when conditions are not met. For instance, XCT assert equal compares two values to ensure they are equal, while XCT assert true verifies that a Boolean condition is true. Similarly, XCT assert nil checks if a value is null, which is useful for validating object references in cases where a test should fail explicitly. XCT fail can be used to mark a test as unsuccessful. Additionally, XCT unimplemented is helpful for marking tests that have not yet been implemented, serving as a reminder to complete the test logic later. These assertions form the backbone of test validation. Organizing tests effectively is crucial for maintaining a scalable and manageable test suite. Related tests should be grouped within the same test class to ensure logical cohesion. The setup method can be used to initialize shared data or configurations, reducing redundancy across test methods. It is important to avoid dependencies between tests, as this can lead to unpredictable results when tests are run in different orders. For asynchronous operations, such as network requests or background tasks, XCT wait for expectations is used to wait for completion before asserting results. This approach ensures that tests accurately reflect the behavior of the code under varying conditions. Adhering to best practices in unit testing ensures that tests remain useful and maintainable over time. One key practice is test-driven development, where tests are written before the actual code, guiding the implementation process. Each test should focus on a single behavior, keeping it isolated and easy to debug. Using descriptive names for test methods helps clarify their purpose, making it easier for other developers to understand the test logic. Regularly running tests throughout the development cycle helps catch issues early and ensures that the code base remains stable. By following these principles, developers can create a reliable and efficient testing workflow. Unit testing with XC test is an essential component of developing high-quality Objective-C applications. By creating structured test cases, developers can verify the correctness of their code and improve overall reliability. Well-organized tests facilitate collaboration among team members and simplify the debugging process. Following best practices ensures that tests remain maintainable and adaptable as the project evolves. Ultimately, continuous testing contributes to the long-term success of software by minimizing errors and fostering confidence in the code base. Embracing unit testing as a standard practice is a valuable investment in software quality. Performance optimization in Objective-C refers to the process of improving the efficiency and speed of an application to ensure it runs smoothly and uses system resources effectively. This involves writing code that minimizes delays, reduces memory consumption, and maximizes the responsiveness of the app. Efficient code is crucial because it directly impacts user experience. If an app is slow or consumes too much memory, users may abandon it. Common performance bottlenecks in Objective-C applications include excessive memory usage, inefficient algorithms, and improper use of object-oriented features like KVC or KVO. Addressing these issues can lead to faster execution and a more stable app. Automatic reference counting is a compiler feature that automatically manages memory by inserting retain and release calls. Using ARC effectively means understanding when and how it handles object life cycles. However, it is not a silver bullet. Retain cycles can occur when two or more objects hold strong references to each other, preventing them from being deallocated. To avoid this, use weak references for delegate relationships or parent-child hierarchies. Releasing unused objects promptly is also essential. For example, setting a strong reference to nil when it is no longer needed ensures that memory is freed up as soon as possible, reducing the risk of memory leaks. Xcode Instruments is a powerful toolset for profiling applications. The Leaks tool helps identify memory leaks by tracking objects that are not properly released. time profiler provides insights into CPU usage, highlighting which functions take the most time to execute. The allocations tool shows how memory is being used over time, helping to spot unnecessary object creation. By using these tools, developers can pinpoint specific areas of the code that need optimization. For instance, a memory leak might be traced to a delegate that is not set to nil, while a CPU bottleneck could be caused by an inefficient loop. Minimizing unnecessary method invocations can significantly improve performance. Each method call involves overhead, such as stack allocation and parameter passing. In performance-critical sections, reducing the number of method calls can lead to faster execution. Key value coding and key value observing are convenient, but can be slower than direct property access. For example, accessing a property directly with .syntax is faster than using value for key or add observer with a key path. Direct method calls are also more predictable and easier for the compiler to optimize. Nested loops can drastically increase the time complexity of an algorithm. For example, a loop inside another loop can lead to unsquared time complexity, which becomes problematic as data size grows. Choosing the right data structure is critical. Arrays are efficient for random access, while dictionaries offer faster lookups by key. Pre-computing values instead of recalculating them in loops can save significant time. For instance, if a calculation is repeated in a loop, storing the result in a variable and reusing it is more efficient than performing the same computation each iteration. Auto-release pools manage the life cycle of auto-released objects. In tight loops, creating too many auto-released objects can lead to memory bloat. Limiting the scope of auto-release pools ensures that objects are released sooner. For example, wrapping a loop in an auto-releasable block allows temporary objects to be released after each iteration, preventing memory from accumulating. This is particularly important in long-running loops or when processing large data sets. Reducing the retention of temporary objects helps maintain a lower memory footprint and improves overall performance. Dynamic messaging in Objective-C, such as perform selector or response to selector, introduces overhead because the method is resolved at runtime. Direct method calls are resolved at compile time, making them faster. For example, Calling a method directly with object method is more efficient than using object perform selector at selector method. In performance critical paths, avoiding response to selector is advisable because it requires a runtime check. Instead, use protocols or direct method calls to ensure predictable behavior and reduce overhead. Choosing the right collection type is essential for performance. NS array is immutable and faster for read-only operations, while NS mutable array allows modifications but has higher overhead. NS cache is ideal for temporary data that can be purged when memory is low, making it better suited for caching than NS dictionary. Avoiding unnecessary object creation, such as repeatedly initializing objects in loops, reduces memory allocation and garbage collection overhead. For example, reusing objects or using object pools can minimize the cost of frequent allocations. Concurrency is key to keeping the main thread responsive. Grand Central Dispatch and NS Operation Q allow tasks to be executed in the background, preventing the UI from freezing. Blocking the main thread with long-running operations, such as network requests or heavy computations, leads to a poor user experience. Using dispatch async to offload work to background queues ensures that the main thread remains available for user interactions. However, overusing concurrency can lead to thread contention. So it is important to balance the number of concurrent tasks. Testing performance with real-world data ensures that optimizations address actual user scenarios. For example, simulating heavy data loads or complex interactions helps identify bottlenecks that may not appear in simple test cases. Time profiling reveals which functions are taking the most time, allowing developers to focus on the most impactful areas. Monitoring memory usage during app execution helps detect leaks or excessive allocations. By combining these techniques, developers can make informed decisions about where to apply optimizations. Prioritizing memory efficiency and code clarity ensures that the app is both performant and maintainable. Tools like instruments provide targeted insights, but they should be used in conjunction with good coding practices. Balancing readability and performance means writing clean, understandable code while avoiding unnecessary overhead. For instance, a slightly more verbose but clear method may be preferable to a highly optimized but obscure one. The goal is to create an app that is fast, stable, and easy to maintain over time. Grand Central Dispatch is a powerful technology developed by Apple to handle concurrent operations in Objective-C applications. It allows developers to manage multiple tasks efficiently without getting bogged down by the complexities of low-level thread management. By abstracting the intricacies of threads, GCD enables smoother execution of tasks, whether they are simple background operations or complex parallel processes. This abstraction not only improves performance, but also reduces the likelihood of errors that often arise in multi-threaded environments. Understanding GCD is essential for creating responsive and efficient iOS and macOS applications. The core components of GCD include queues, dispatch blocks, and dispatch sources. Queues act as the central mechanism for managing task execution, organizing them in a first-in, first-out manner. These queues can be either serial, processing tasks one at a time, or concurrent, allowing multiple tasks to run simultaneously. Dispatch blocks are the actual code snippets that perform the work, and they can be executed asynchronously or synchronously. Dispatch sources, on the other hand, monitor various events such as timers, file system changes, or socket activity, triggering appropriate actions when those events occur. Together, these components form the backbone of GCD's capabilities. GCD queues come in three primary types: the main queue, global queues, and custom queues. The main queue is tied to the application's main thread and is specifically designed for UI updates, ensuring that all interface changes occur on a single thread. Global queues are pre-configured by the system and are used for background tasks, offering different priority levels to manage resource allocation. Custom queues, created by developers, provide flexibility for specific use cases, allowing for tailored task management strategies. Choosing the right queue type is crucial for optimizing application performance. Serial queues and concurrent queues serve distinct purposes in GCD. A serial queue processes tasks in a strict sequence, ensuring that only one task runs at a time. This is particularly useful for operations that require thread safety, such as accessing shared resources. In contrast, concurrent queues execute tasks simultaneously, leveraging multiple cores to improve efficiency. However, this parallelism requires careful handling to to avoid conflicts. Developers must choose between these queue types based on the nature of the tasks, balancing performance gains with the need for controlled execution. Dispatching tasks in GCD is done through two primary functions: dispatch async and dispatch sync. Dispatch async is used for asynchronous execution, allowing the current thread to continue running while the task completes in the background. This is ideal for long-running operations that should not block the user interface. Dispatch sync, on the other hand, executes tasks synchronously, pausing the current thread until the task finishes. While this can be useful for ensuring immediate results, overuse can lead to deadlocks or unresponsive applications. The example provided demonstrates how to dispatch a task to a global queue and then update the UI on the main thread. Synchronizing tasks with GCD involves mechanisms like barrier blocks and dispatch groups. Barrier blocks are used to ensure exclusive access to shared resources, preventing race conditions by temporarily halting other tasks. Dispatch groups, meanwhile, track the completion of multiple tasks, allowing developers to execute a block of code once all tasks are done. This is particularly useful for coordinating complex workflows, such as waiting for several network requests to finish before updating the UI. These tools help maintain data integrity and manage dependencies in concurrent environments. Blocks or closures are fundamental to GCD as they encapsulate tasks for execution. They can capture variables from their surrounding scope, making them versatile for handling dynamic data. However, when a block needs to modify a variable outside its scope, the block keyword is used to indicate that the variable should be mutable. This feature enables blocks to interact with their environment while maintaining control over data changes. Understanding how blocks capture and manipulate variables is essential for writing effective and safe concurrent code. The example code illustrates how to perform an asynchronous task using GCD. By dispatching a block to a global queue, the application can execute background operations without freezing the user interface. Once the task completes, the code uses dispatch async again to return to the main queue and update the UI. This pattern is critical for maintaining a responsive application, as it separates time-consuming processes from the main thread. Developers should always ensure that UI updates occur on the main thread to avoid unpredictable behavior and ensure thread safety. Adhering to best practices when using GCD can significantly enhance application performance and stability. Overusing GCD for simple tasks may introduce unnecessary overhead, so it's important to evaluate whether concurrency is truly needed. Serial queues are invaluable for protecting shared resources, preventing conflicts that can arise from simultaneous access. Finally, always prioritize the main queue for UI updates to maintain a seamless user experience. These guidelines help developers strike the right balance between efficiency and maintainability in their code. In summary, GCD is a cornerstone of concurrency management in Objective-C, offering tools to streamline task execution and improve application performance. By mastering queues, blocks, and synchronization techniques, developers can create robust and efficient applications. Applying GCD effectively allows for better resource utilization, easier management of complex task dependencies, and a more responsive user interface. As with any powerful tool, understanding its nuances and best practices is key to unlocking its full potential. Core Data is Apple's framework designed to help developers manage data persistence in iOS and macOS applications. It provides a robust solution for handling complex data models, allowing you to work with objects rather than directly interacting with databases. This framework not only stores data, but also manages the relationships between different data entities, making it easier to handle interconnected information. Key features include data modeling, which lets you define your data structure visually, relationships that link different data elements, and efficient querying mechanisms to retrieve data quickly. By using Core Data, developers can focus more on building application logic rather than worrying about the underlying storage details. The Core Data framework consists of several key components that work together to manage data. The Managed Object Model serves as the blueprint for your data, defining entities, attributes, and relationships. This model is created using Xcode's data model editor, where you can visually design your data structure. The Persistent Store Coordinator acts as a bridge between the model and the actual storage, such as SQLite or an in-memory store. It handles the communication between the data model and the physical storage. The Managed Object Context functions as a temporary workspace where you interact with your data. It allows you to create, modify, and delete objects before saving them to the persistent store. Together, these components form the foundation of core data's functionality. Setting up core data begins with creating a data model file, which has the extension xcdatamodeled. This file is where you define your data structure. To start, you add entities, which represent the different types of data your app will handle, such as person or task. Each entity has attributes that define its properties, like name, age, or date. Relationships between entities can also be established, such as a person entity having multiple tasks. Xcode provides templates to generate managed object subclasses, which are Objective-C classes that represent your entities. These classes allow you to work with your data in a type-safe manner, reducing errors and improving code readability. Properly setting up these elements ensures a solid foundation for your app's data management. The core data stack is a critical architecture that connects the model, store, and context. The model, as mentioned earlier, defines the structure of your data. The store is where the data is physically stored, such as in an SQLite database or in a memory store. The context is where you perform all your data operations, like creating, updating, or deleting objects. This stack ensures that data flows seamlessly between these components, allowing your app to persist data efficiently. Understanding how these parts interact is essential for building reliable applications. The stack acts as a pipeline, ensuring that changes made in the context are saved to the store, and that data retrieved from the store is properly represented in the model. Entities in core data are the building blocks of your data model, representing real-world objects or concepts. For example, an entity named person might have attributes like name, age, and date of birth. Relationships allow entities to be connected, such as a person entity having a one-to-many relationship with a task entity. These relationships can be configured as to one or to many, depending on the data structure. Defining entities and their attributes requires careful planning to ensure your data model accurately reflects the needs of your application. By organizing your data into entities, you can create a structured and maintainable data system that scales with your app's complexity. Saving data in core data involves making changes to objects within the managed object context, and then committing those changes to the persistent store. When you modify an object, such as updating a person's name or adding a new task, these changes are stored in the context. To persist them, you call the save method on the context, which writes the changes to the store. However, saving can fail, so it's important to handle errors using NS-error. This ensures that any issues, such as disk space problems or invalid data, are addressed gracefully. Proper error handling is crucial for maintaining data integrity and providing a smooth user experience. Always check the result of the save operation to confirm that your data has been successfully stored. Fetching data from core data requires using an NS fetch request object, which specifies the type of data you want to retrieve. You can filter results using predicates, which are like search conditions that narrow down the data. For example, you might fetch all tasks with a specific status or all people older than a certain age. Sorting and limiting results is also possible by adding sort descriptors to the fetch request. These descriptors determine the order of the results and can be used to display data in a user-friendly way. By mastering NS fetch request, you can efficiently retrieve the data your app needs, ensuring optimal performance and usability. Updating and deleting data in core data follows a similar process to saving. To update an object, you modify its attributes within the managed object context. For example, you might change a person's email address or update a task's completion status. Once the changes are made, you save the context to persist them. Deleting data involves using the delete object method on the context, which marks an object for deletion. However, the actual deletion occurs when you save the context. It's important to remember that deleted objects are no longer accessible after the save operation. Properly managing updates and deletions ensures your data remains accurate and consistent across your app's lifecycle. While core data is powerful, it's easy to encounter common pitfalls. One frequent mistake is forgetting to save changes to the context, which results in data being lost when the app closes. Another issue is incorrectly setting up relationships between entities, leading to data inconsistencies or crashes. Memory leaks can also occur if contexts or objects are not properly released, especially in complex applications. To avoid these issues, always verify that your save operations are successful. Double-check relationship configurations and use tools like Xcode's memory debugger to identify leaks. Being mindful of these challenges helps ensure a stable and reliable data management system. In conclusion, core data is a vital tool for managing data persistence in Apple's platforms, offering a comprehensive solution for handling complex data structures. Understanding its components and workflow is essential for building efficient and scalable applications. By practicing with real-world examples, such as managing user profiles or tracking tasks, you can gain hands-on experience and deepen your expertise. As you continue to explore core data, you'll discover its full potential to streamline data management and enhance the functionality of your apps. Keep experimenting and refining your skills to master this powerful framework. iCloud is a powerful tool that allows users to seamlessly synchronize their data across all Apple devices. This means that whether someone is using an iPhone, iPad, or Mac, their documents, data, and user preferences remain consistent and up to date. For developers working with Objective-C, iCloud integration is made possible through two key components: CloudKit and NS Metadata Query. CloudKit serves as the backend for storing and retrieving data, while NS Metadata Query helps monitor changes to files and documents. Together, these tools enable a robust and efficient way to handle data synchronization in Objective-C applications. Before diving into iCloud integration, there are several prerequisites that must be addressed. First, you need an Apple developer account, which grants access to the necessary tools and services. Next, in Xcode, you must enable the iCloud capability under the project's signing and capabilities settings. This step ensures that your app is configured to use iCloud services. Additionally, you must configure the entitlements file properly, which specifies the permissions and access levels your app requires. These steps are crucial for ensuring that your app can communicate with iCloud and handle user data securely. iCloud offers several key services that developers can leverage. The first is CloudKit, which acts as a backend for storing and retrieving data. It allows you to create databases, manage records, and query data efficiently. Another service is UI Document, which is specifically designed for managing document storage and synchronization. By subclassing UI Document, you can handle file operations and ensure that changes are automatically synced across devices. Finally, there is the option to use NS user defaults with iCloud, which allows user preferences to be synchronized across devices. However, this approach has limitations and is best suited for smaller data sets. Setting up iCloud in Xcode involves a few straightforward steps. Begin by navigating to the Signing and Capabilities section of your project settings. From there, add the iCloud capability, which will prompt you to select the appropriate containers for your app. Containers are essentially storage areas that hold your app's data. Once the capability is added, ensure that the entitlements file is correctly configured for your target. This file defines the permissions and access rights required for iCloud operations. Proper configuration at this stage is essential to avoid runtime errors and ensure smooth functionality. CloudKit integration begins with the CK container class, which provides access to the user's iCloud storage. Each container can have multiple databases, and the CK database class is used to perform operations such as saving, querying, and retrieving data. Within a database, data is stored as records, which are represented by the CK record class. These records can contain various types of data, including text, images, and binary files. By using these classes, developers can build applications that leverage iCloud's backend to store and manage user data efficiently. Document synchronization in Objective-C is typically handled using the UI document class. By creating a subclass of UI document, you can define how your app reads from and writes to files. The save method allows you to persist changes to the document, while the completion handler ensures that the sync process is properly managed. To monitor changes in real time, NS metadata query is used. This class allows you to track file modifications and updates, ensuring that your app stays in sync with the latest data across all devices. This combination of UI document and NS metadata query provides a powerful solution for managing document-based applications. When it comes to key value storage with iCloud, the NS User Defaults class offers a convenient way to sync user preferences. By calling the synchronize method, you can ensure that changes to user defaults are immediately saved to iCloud. However, it's important to note that this approach has limitations. The size of data stored in NS user defaults is constrained, and performance can degrade with large datasets. Additionally, it's not advisable to store sensitive or large amounts of data in this manner. For such cases, developers should consider alternative methods like CloudKit or custom file storage solutions. Security and privacy are paramount when working with iCloud. All data transmitted through iCloud is encrypted in transit, and data stored on Apple's servers is also encrypted at rest. Users must have an active iCloud account and be signed in with their Apple ID to access these services. As a developer, it's essential to handle user authentication and permissions gracefully. This includes providing clear prompts for users to enable iCloud and managing any errors that may arise from incorrect or missing permissions. Ensuring a smooth and secure experience is key to building trust with your users. Error handling and debugging are critical aspects of iCloud integration. Common issues include network connectivity problems, insufficient permissions, and exceeding storage quotas. By using NS error objects, you can capture and handle these errors effectively, providing meaningful feedback to users. It's also important to test your app on real devices rather than simulators, as iCloud behavior can differ significantly between the two. Debugging tools like the iCloud console and Xcode's built-in diagnostics can help identify and resolve issues before they affect end users. Testing iCloud integration requires a systematic approach. The iCloud console provides a way to monitor data stored in your app's containers, allowing you to verify that synchronization is working as expected. Simulating network changes and user sign-in states can help ensure your app handles these scenarios gracefully. Finally, it's essential to test across multiple devices to confirm that data is consistently synchronized. These steps help identify potential issues and ensure a reliable user experience. Following best practices is crucial for effective iCloud integration. One key recommendation is to minimize the size of data being synced, as larger files can slow down the process and consume more bandwidth. When conflicts arise, such as when the same data is modified on multiple devices, using timestamps or versioning can help resolve discrepancies. Additionally, providing clear user feedback about sync status, such as progress indicators or notifications, enhances the overall user experience. These practices contribute to a more efficient and user-friendly application. In conclusion, iCloud significantly enhances the user experience by enabling seamless data access across devices. Objective-C provides a robust set of tools, including CloudKit, UI Document, and NS user defaults, to facilitate this integration. However, it's essential to prioritize security, thorough testing, and a user-centric design approach. By following best practices and addressing potential challenges, developers can create applications that leverage iCloud effectively while maintaining performance, reliability, and user trust. The observer pattern is a behavioral design pattern that defines a one-to-many dependency between objects. This means that when one object, known as the subject, changes its state, all its dependents, referred to as observers, are automatically notified and updated. This pattern is particularly useful in scenarios where objects need to communicate without being tightly coupled. For example, imagine a weather monitoring system where multiple displays need to update whenever the weather data changes. The key components of this pattern include the subject, which maintains a list of observers and notifies them of changes, the observer, which defines an interface for updating the state, and the concrete subject and concrete observer, which are the specific implementations of these roles. This structure promotes loose coupling and makes the system more flexible and scalable. In Objective-C, the observer pattern is implemented through two primary mechanisms: delegation and notifications. Delegation establishes a direct relationship between objects, where one object acts on behalf of another. For instance, a UI text field might delegate its text change events to a delegate object, allowing the delegate to handle the update. On the other hand, notifications provide a more decentralized approach using the NS Notification Center class. This allows objects to broadcast messages to any number of observers without needing direct references to them. For example, a UI text field can notify its delegate of text changes via delegation, while a notification might be used to inform multiple parts of an app about a significant event like user login. Both approaches have their use cases, and the choice between them depends on the level of control and coupling required. Notifications in Objective-C are a powerful tool for enabling communication between objects through the NS Notification Center. This class allows objects to broadcast messages, known as notifications, to interested observers. The key methods involved in this process include add observer, which registers an observer to listen for specific notifications, post notification name, which sends a notification to all registered observers, and remove observer, which unregisters an observer to prevent unnecessary updates. Each notification has a unique name, an optional object, and user information that can carry additional data. By using these methods, developers can create a flexible system where any part of the code can send or receive notifications, making it ideal for scenarios where multiple components need to respond to the same event. The advantages of using notifications in Objective-C are significant. First, they promote decoupling, meaning that objects do not need to have direct references to each other, which simplifies maintenance and reduces dependencies. Second, notifications enhance scalability, as multiple observers can listen to the same notification and respond independently. This makes it easy to add new observers without modifying existing code. Finally, notifications offer flexibility, allowing messages to be posted from any part of the application. For example, a background process can notify the user interface to update its state, even if the two are not directly connected. This makes notifications a versatile choice for managing communication in complex applications. However, notifications also come with several disadvantages that developers must be aware of. One major challenge is debugging, as the flow of notifications can be difficult to trace, especially in large applications with many observers. This can lead to unexpected behavior that is hard to diagnose. Another issue is memory leaks, which occur when observers are not properly removed. If an observer is not unregistered, it may continue to receive notifications even after the object it was observing has been deallocated, leading to retained cycles. Additionally, excessive use of notifications can introduce performance overhead, as each notification requires processing and may slow down the application. Therefore, it is crucial to use notifications judiciously and manage them carefully. When comparing the observer pattern and notifications in Objective-C, the key differences lie in their approach to communication. The observer pattern, often implemented through delegation, provides tighter control and direct communication between objects. This is ideal for scenarios where a specific object needs to handle updates, such as a view controller managing a table view's data. In contrast, notifications offer a looser coupling, allowing multiple observers to respond to the same event. This is useful for broadcasting updates across the application, such as notifying all relevant components of a user's login. The choice between the two depends on the specific requirements of the application, with delegation being more suitable for direct interactions and notifications for broader, broadcast-based communication. Let me walk through a practical example of using notifications in Objective-C. The first step is to add an observer using the Add Observer method. For instance, the code NS Notification Center Default Center Add Observer Self Selector at Selector Handle Notification. Name at my notification object. Nil registers the current object to listen for a notification named My Notification. When this notification is posted, the handle notification method is called, allowing the object to respond. To trigger the notification, the code NS Notification Center Default Center Post Notification Name at my notification object nil user info at key. At value sends the message, passing along user information in a dictionary. The handle notification method can then extract this data and update the user interface or perform other actions. This example demonstrates how notifications can be used to decouple components and enable asynchronous communication. To ensure effective use of notifications in Objective-C, it is essential to follow best practices. First, always remove observers in the dealloc method, or when they are no longer needed, such as in View Will Disappear, to prevent memory leaks and retain cycles. Second, use unique notification names to avoid conflicts, especially in larger applications where multiple components might use similar names. Third, avoid performing heavy computations in notification handlers, as this can block the main thread and degrade performance. Finally, consider using blocks instead of selectors for modern Objective-C code, as they provide a more concise and readable way to handle notifications. By adhering to these practices, developers can create more maintainable and efficient applications. In conclusion, the observer pattern and notifications are essential tools for enabling efficient communication in Objective-C. The observer pattern provides a structured way to manage dependencies between objects, while notifications offer a flexible, broadcast-based approach. Choosing between them depends on the specific needs of the application, with notifications being ideal for loose coupling and broadcasting, and delegates for direct, controlled interactions. It is crucial to prioritize memory management and clarity when implementing observers, ensuring that the application remains responsive and scalable. By understanding the strengths and limitations of each approach, developers can make informed decisions that enhance the overall architecture of their code. To summarize, the observer pattern decouples objects by establishing dependencies that allow for automatic updates. Notifications, facilitated by NS Notification Center, enable broadcasting updates across the application, making them a powerful tool for asynchronous communication. When choosing between these patterns, it is important to balance flexibility and performance, ensuring that the solution fits the specific requirements of the project. By following best practices such as proper observer management and unique notification naming, developers can avoid common pitfalls and create robust, maintainable code. This understanding of the observer pattern and notifications is fundamental for building efficient and scalable Objective-C applications. Design patterns are reusable solutions to common software design problems. They provide proven approaches to structuring code for flexibility and maintainability. By using design patterns, developers can avoid reinventing the wheel and instead apply time-tested strategies to solve recurring challenges. Objective-C supports design patterns through its object-oriented features, which include classes, inheritance, and polymorphism. These features allow developers to implement patterns like the factory pattern, which helps manage object creation in a more organized and scalable way. Understanding design patterns is essential for writing clean, efficient, and maintainable code in any programming language, and Objective-C is no exception. A creational pattern that defines an interface for creating objects, delegates object creation to subclasses or helper classes, avoids tight coupling between classes and their dependencies. The factory pattern is a creational design pattern, meaning it focuses on the process of object creation rather than the structure of the objects themselves. By defining a common interface for creating objects, the factory pattern allows different implementations to handle the actual creation. This delegation of responsibility to subclasses or helper classes makes the code more modular and easier to extend. For example, if a class needs to create multiple types of objects, the factory pattern can encapsulate the logic for determining which type to create, reducing the need for conditional statements in the main code. This approach also prevents tight coupling, where one class becomes overly dependent on another, making the system more flexible and easier to maintain. Simple factory. A single class handles object creation. Factory method. Subclasses decide which class to instantiate. Abstract factory creates families of related objects. The simple factory is the most straightforward implementation, where a single class contains logic to create different types of objects. This is useful when the creation process is centralized and relatively simple. The factory method, on the other hand, allows subclasses to determine the type of object to create. This is particularly useful when a class cannot anticipate the exact type of objects it needs to create. The abstract factory goes a step further by providing an interface for creating families of related objects. For instance, an abstract factory might create a set of UI components that are consistent with a specific theme, ensuring that all elements work together seamlessly. Each of these variations offers different levels of flexibility and complexity, making them suitable for different scenarios. Define a factory method in a class to return instances. Example: plus I'd create object with type ns string type. Use alloc and init internally to encapsulate object creation logic. Implementing the factory pattern in Objective-C involves creating a method that acts as a central point for object creation. This method, often a class method, takes parameters such as a type or configuration and returns an instance of the appropriate class. For example, a method like plus I'd create object with type ns string type might check the input type and then use alloc and init to instantiate the corresponding object. By encapsulating the creation logic within the factory method, the rest of the code base remains decoupled from the specific implementation details. This not only simplifies the code, but also makes it easier to modify or extend the creation process without affecting existing code. Encapsulates object creation logic, improves code maintainability and scalability, facilitates testing with mock objects. One of the key benefits of the factory pattern is that it encapsulates object creation logic, making the code more organized and easier to manage. Instead of scattering creation logic throughout the code base, it is centralized in a single location. This improves maintainability because changes to the creation process only need to be made in one place. It also enhances scalability, as adding new types of objects becomes a matter of updating the factory rather than modifying existing code. Additionally, the factory pattern makes testing easier by allowing developers to substitute real objects with mock or stub objects. This is particularly useful in unit testing, where controlled environments are necessary to verify behavior without relying on external dependencies. Creating UI components dynamically, e.g., buttons, views, managing different data sources, e.g., JSON, XML, supporting plugin architectures or modular systems. The factory pattern has numerous real-world applications, especially in scenarios where objects need to be created dynamically. For instance, in user interface development, a factory can generate different types of UI components based on user input or configuration settings. This is common in applications that need to adapt their layout or behavior at runtime. Similarly, when working with data sources, a factory can handle the creation of objects from different formats, such as parsing JSON or XML data into appropriate model classes. The pattern is also valuable in plugin architectures or modular systems, where new components can be added without modifying existing code. By abstracting the creation process, the factory pattern enables systems to remain flexible and extensible over time. Factory pattern simplifies object creation and enhances flexibility. Design patterns like factory are essential for scalable Objective-C projects. Apply these concepts to improve code structure and reusability. The factory pattern is a powerful tool for simplifying object creation and improving the overall structure of an application. By reducing dependencies and centralizing creation logic, it makes code more flexible and easier to manage. Design patterns like the factory pattern are not just theoretical concepts. They are essential for building scalable and maintainable Objective-C projects. Whether you are developing a small application or a large-scale system, applying these principles can lead to cleaner code, better organization, and more efficient development processes. As you continue your journey with Objective-C, remember to leverage design patterns to create robust and reusable solutions. Error handling in Objective-C is a critical aspect of developing reliable and stable applications. Unlike languages such as Java or C++ that utilize try-catch blocks for exception handling, Objective-C takes a different approach by relying on NS error objects to represent and manage errors. This design choice allows developers to encapsulate detailed error information, making it easier to diagnose and respond to issues during runtime. Understanding how to effectively handle errors is essential for building robust applications that can gracefully recover from unexpected situations. By focusing on NS error, developers can create more maintainable code that clearly communicates errors between different parts of the program. The NS error class serves as the primary mechanism for representing errors in Objective-C. It is designed to hold three key components: a domain, a code, and a user info dictionary. The domain is a string that identifies the source of the error, such as NS Coco error domain for system-level errors. The code is an integer that specifies the exact nature of the error within the domain. The user info dictionary provides additional context, such as localized messages or related objects, which can be invaluable for debugging. By using NS error, developers can pass error information across method calls, ensuring that errors are not lost and can be addressed at the appropriate level of the application. Creating and using NS error is a straightforward process that involves either manually initializing an error object or relying on methods that return errors. For example, developers can create an error with a custom domain, code, and user info dictionary to represent specific issues within their application. Methods often accept an NS error pointer as an argument, allowing them to populate this pointer with error details if something goes wrong. This approach requires careful handling, as developers must always check for nil or error values after method calls. Ignoring errors can lead to unexpected behavior, so it is crucial to implement proper error checking mechanisms to ensure the program remains stable. Error propagation in Objective-C is achieved by passing NS error pointers through the call stack. This means that when a method encounters an error, it can set the error pointer to an appropriate NS error object and return a failure status. For instance, a method might check for a specific condition, and if it fails, assign an error to the pointer and return no. This allows the calling method to handle the error, whether by logging it, displaying a message to the user, or taking corrective action. By propagating errors in this manner, developers can create a clear and structured way to manage issues, ensuring that no error goes unnoticed and that the application can respond appropriately at each level. While Objective-C does not use try-catch blocks for error handling, it does support exception handling through the @try, @catch, and @finally constructs. Exceptions are primarily used for unrecoverable errors, such as programming mistakes or critical failures that cannot be resolved during runtime. For example, if a method is called with invalid parameters, an exception might be thrown to signal the problem. The @try block contains the code that may throw an exception. The @catch block handles the exception, and the @finally block executes cleanup code regardless of whether an exception occurred. However, exceptions should be reserved for truly exceptional circumstances, as they are not designed for normal error scenarios. Exceptions in Objective-C are best suited for situations where a program cannot continue executing normally. This includes programming errors such as invalid input, null pointers, or other critical failures that require immediate attention. However, it is important to avoid using exceptions for regular error conditions, such as file not found or network issues, which are better handled with NS error. Exceptions also come with a performance cost, as their handling involves additional overhead. Therefore, they should be used sparingly and only for scenarios where recovery is not feasible. By distinguishing between exceptions and NS error-based errors, developers can create more efficient and maintainable code. Adhering to best practices in error handling is essential for writing high-quality Objective-C code. For recoverable errors and user-facing issues, developers should prioritize the use of NS error, as it provides a structured and flexible way to communicate errors. Exceptions, on the other hand, should be reserved for truly exceptional conditions that cannot be handled through normal error mechanisms. It is also important to always check for errors explicitly, as ignoring NS error pointers can lead to undefined behavior or crashes. Additionally, documenting error domains and codes helps other developers understand the context of errors, making the code base more transparent and easier to maintain. By following these guidelines, developers can ensure their applications are both robust and user-friendly. In conclusion, error handling in Objective-C is primarily based on the use of NS error objects, which provide a detailed and structured way to represent and propagate errors. While exception handling is available, it is intended for critical issues that cannot be recovered from, rather than for normal error scenarios. Proper error management is vital for ensuring application stability, improving user experience, and making code more maintainable. By choosing the right approach for each situation and following best practices, developers can create applications that are resilient to unexpected issues and provide a seamless experience for users. Always prioritize clarity and robustness when designing error handling mechanisms. Unit testing is a crucial practice in software development that involves verifying individual components of code to ensure they function correctly. By testing each part of a program in isolation, we can identify issues early and confirm that the code behaves as expected under various conditions. This approach significantly reduces the likelihood of bugs and enhances the overall reliability of the application. In the context of Objective-C, the XC test framework serves as the primary tool for implementing unit tests. XC test provides a structured environment for writing and executing tests, making it an essential component for developers working within the Apple ecosystem. The benefits of unit testing extend far beyond simple error detection. One of the most significant advantages is that it facilitates early bug detection, allowing developers to address issues before they escalate into larger problems. This proactive approach simplifies debugging and maintenance, as each test case isolates specific functionality, making it easier to trace and fix issues. Additionally, unit testing enables confident code refactoring, as developers can modify existing code without fear of breaking functionality, provided the tests remain passing. Furthermore, well-written tests act as a form of documentation, illustrating how different parts of the code base are intended to work. This makes it easier for new team members to understand and contribute to the project. The XC test framework is Apple's built-in solution for unit testing in Objective-C and other Apple languages. It offers a comprehensive set of tools, including assertions, test cases, and test suites, to help developers create robust tests. Assertions are used to verify conditions, such as whether a value matches an expected result. Test cases represent individual scenarios, while test suites organize multiple test cases into groups for efficient execution. Tests written with XCTest can be run directly from Xcode's Test Navigator, providing a streamlined workflow for developers. To create a test, you must subclass XCTestCase, which serves as the foundation for all test classes. This structure ensures consistency and makes it easier to manage and execute tests. Writing a unit test in Objective-C involves creating a test class that inherits from XCTestCase. This class contains methods that represent individual test cases, typically named with a prefix, such as test example, to indicate their purpose. These methods use XCT assert macros to validate the expected outcomes of the code being tested. For instance, the macro XCT assert equal checks whether two values are equal, while XCT assert true confirms a condition is true. An example of this is the test case where we verify that adding 1 plus 1 results in 2. This simple check ensures that the code behaves as intended and serves as a foundation for more complex tests. By using these macros, developers can quickly and effectively validate their code's behavior. Test-driven development, or TDD, is a development methodology that emphasizes writing tests before implementing the actual code. This approach follows the red-green refactor cycle, which consists of 3 key steps. First, the red phase involves writing a test that initially fails because the required functionality does not yet exist. Next, the green phase requires writing the minimal amount of code necessary to make the test pass. Finally, the refactor phase focuses on improving the code's structure and efficiency without altering its behavior. This iterative process ensures that the code is designed with testability in mind, leading to cleaner and more maintainable code. TDD also encourages developers to think about the requirements and edge cases before writing any implementation. The TDD workflow in Objective-C follows a structured sequence to ensure code quality. It begins by defining the requirements and writing test cases that capture the expected behavior of the code. These tests are then run to confirm they fail, as the implementation does not yet exist. Once the tests are in place, developers implement the code to satisfy the test cases, ensuring that each test passes. After the code is functional, the refactor phase involves improving the design and performance of the code while maintaining the passing tests. This cycle is repeated throughout the development process, ensuring that the code remains robust and adaptable to future changes. By following this workflow, developers can build applications that are both reliable and easy to maintain. An example of a test case in Objective-C involves verifying the correctness of a method, such as add numbers and, which takes two integers and returns their sum. The test case would call this method with specific values, such as 2 and 3, and use an assertion to check that the result is 5. This ensures that the method behaves as expected under normal conditions. However, it is equally important to test edge cases, such as when one or both numbers are 0 or negative. For instance, a test might check that adding 0 and 5 results in 5, or that adding and 4 yields 1. By covering these scenarios, developers can ensure that their code handles all possible inputs gracefully, reducing the risk of unexpected behavior in real-world applications. To write effective tests, developers should adhere to several best practices. First, tests should be isolated and independent, meaning that each test should not rely on the state of other tests. This prevents cascading failures and ensures that tests can be run in any order. Descriptive test names are also critical, as they clearly indicate what is being tested and what outcome is expected. For example, a test named test add numbers with positive values provides immediate clarity about its purpose. Developers should focus on testing public interfaces rather than private methods, as the latter may change frequently and are not part of the external API. Finally, it is important to balance test coverage with readability, ensuring that tests are comprehensive without becoming overly complex or difficult to maintain. Despite its benefits, unit testing can present challenges if not approached carefully. One common pitfall is overlooking edge cases, which can lead to unhandled scenarios in production. For example, a test that only checks positive numbers may fail when negative values are provided. Another issue is testing implementation details rather than the outcome outcomes of the code. This makes tests brittle, as changes to the internal logic can cause tests to break even if the behavior remains correct. Additionally, tests that are too tightly coupled to the code's structure can become fragile, requiring frequent updates as the code evolves. Lastly, neglecting test maintenance can result in outdated tests that no longer reflect the current code base, leading to false positives or negatives. Addressing these pitfalls requires careful planning and regular review of the test suite. In conclusion, unit testing is a fundamental practice that significantly improves the quality and maintainability of software. By verifying individual components of code, developers can identify and resolve issues early, leading to more reliable applications. Test-driven development further enhances this process by promoting a disciplined approach to coding, ensuring that tests guide the implementation. The XC test framework is an indispensable tool for Objective-C developers, providing the necessary infrastructure to automate testing within Xcode. As with any skill, the key to mastering unit testing lies in consistent practice and a commitment to writing tests that are clear, effective, and maintainable. By integrating these practices into their workflow, developers can build robust applications that stand the test of time. Objective-C and Swift can coexist in the same project, allowing developers to leverage the strengths of both languages. This interoperability is essential for maintaining legacy code bases while adopting modern practices. By sharing code, libraries, and frameworks between the two languages, teams can gradually transition from Objective-C to Swift without rewriting entire applications. Apple actively supports this integration, ensuring that developers can seamlessly combine older code with new Swift implementations. This flexibility is particularly valuable for large projects that require incremental updates. A fundamental aspect of interoperability is the ability to use Objective-C classes in Swift through a process called bridging. This involves exposing Objective-C code to Swift via a bridging header, which allows Swift to recognize and utilize the imported classes and methods. Conversely, Swift types can interact with Objective-C APIs through automatic conversion, making it easier to integrate new Swift code with existing Objective-C systems. However, it is important to note that the Objective-C runtime supports dynamic behavior, which differs from Swift's emphasis on safety and performance. Understanding these distinctions helps developers navigate potential challenges when working across both languages. To enable interoperability, developers must create a bridging header file with a H extension. This file acts as a gateway, allowing Swift to access Objective-C code by importing the necessary headers. Configuring the project's build settings is a critical step, as the Objective-C bridging header setting must point to the correct header file. For example, adding import myClassH to the bridging header makes the myClass class available in Swift. This setup ensures that Objective-C code can be seamlessly integrated into Swift projects, preserving functionality while enabling modernization. Once a bridging header is properly configured, Swift automatically imports the Objective-C headers, making it straightforward to use Objective-C classes and methods directly within Swift code. This direct access simplifies the integration of legacy code into new projects. However, developers should be aware of certain limitations. For instance, some Objective-C features like blocks and selectors require explicit handling in Swift, as they do not map directly to Swift syntax and type system. Understanding these nuances ensures smoother interactions between the two languages. When moving from Swift to Objective-C, developers must use the addObject attribute to expose Swift classes and methods to Objective-C. This attribute allows Swift code to be recognized by the Objective-C runtime, enabling interoperability. Swift enums and structs can also map to Objective-C equivalents, though care must be taken to ensure compatibility. For example, marking an enum with addObject and specifying an underlying type like int ensures it can be used in Objective-C. This process highlights the importance of aligning Swift constructs with Objective-C expectations, facilitating seamless communication between the two languages. Interoperability between Objective-C and Swift is not without its challenges. Type mismatches often arise due to differences in how the two languages handle data types, requiring developers to manually adjust conversions. Memory management is another key issue, as Objective-C traditionally uses manual reference counting, while Swift relies on automatic reference counting. These differences can lead to unexpected behavior if not carefully managed. Additionally, naming conventions and method signatures may need adjustment to align with Objective-C's style, ensuring that functions and classes are accessible and usable across both languages. To navigate these challenges effectively, developers should follow best practices for interoperability. Using bridging headers is recommended for large Objective-C code bases, as it provides a structured way to expose code to Swift. Minimizing direct interactions between the two languages helps reduce complexity and potential errors. Thorough testing is also crucial, especially when dealing with complex data types or edge cases. By adhering to these practices, developers can maintain a stable and maintainable code base that balances the benefits of both Objective-C and Swift. Interoperability remains a critical component of modernizing Objective-C projects, allowing teams to harness Swift's safety and performance while preserving existing code. By strategically integrating the two languages, developers can create robust applications that evolve over time. Prioritizing modular design ensures that future transitions are smoother, as individual components can be updated independently. This approach not only simplifies maintenance, but also prepares projects for long-term success in a rapidly changing development landscape. Objective-C memory management fundamentals form the backbone of efficient application development. Understanding how objects are allocated, retained, and released is crucial for preventing memory leaks and ensuring smooth performance. In iOS apps, where resources are limited, efficient memory usage directly impacts user experience, app stability, and battery life. By mastering advanced techniques such as auto-release pools, weak references, and custom memory handling, developers can optimize their code to handle complex data structures and long-running operations without compromising system resources. These techniques not only improve app responsiveness, but also align with Apple's guidelines for high-quality software. Retain cycles occur when two or more objects hold strong references to each other, creating a loop that prevents them from being deallocated. This is a common issue in object relationships, such as when a delegate or a block retains its owner. Strong references, while essential for maintaining object lifetimes, can inadvertently lead to memory leaks if not managed carefully. To identify retained cycles, developers can use tools like like instruments or analyze object retain counts. Breaking these cycles often involves using weak or unretained references, particularly in scenarios like delegation or closures, to ensure that objects are released when no longer needed. Auto-release pools play a critical role in managing temporary objects by deferring their release until the end of the current run loop. This is especially useful in scenarios where many short-lived objects are created, such as in loops or during heavy computations. Nested auto-release pools allow developers to control the scope of object deallocation, reducing memory peaks and improving performance. For example, in a loop that generates numerous temporary objects, wrapping the loop in an auto-release pool ensures that memory is freed incrementally rather than all at once. Avoiding excessive memory usage during heavy operations requires careful placement of auto-release pools and understanding their interaction with the run loop. Using weak references is a powerful strategy to prevent retained cycles, particularly in delegate patterns. Delegates often hold strong references to their owners, which can lead to memory leaks if not addressed. By declaring delegates as weak, the reference does not increase the retained count of the delegate, allowing the owner to be deallocated when necessary. Safe practices include checking for nil before accessing weakly referenced objects, as they may have been released. For instance, in UI kit components like UI table view, the delegate is typically declared as weak to avoid cycles. This approach ensures that the delegate relationship remains lightweight and does not hinder the app's memory management. Custom memory management methods involve overriding retain, release, and auto-release to handle specific object lifetimes. This is necessary in cases where the default behavior does not suffice, such as with custom objects or non-Objective-C resources. However, manual memory handling without automatic reference counting arc requires meticulous attention to detail. Developers must ensure that retain and release are balanced, and auto-release is used appropriately to avoid leaks or premature deallocations. The risks of manual management include subtle bugs, such as over-releasing objects or failing to retain necessary references, which can lead to crashes or undefined behavior. The NS Zombie Enabled Environment Variable is a debugging tool that helps identify dangling pointers by replacing deallocated objects with special placeholders. When a message is sent to a zombie object, the app logs a detailed error, making it easier to trace the source of the issue. Instruments, Apple's suite of performance tools, provides advanced leak detection by analyzing heap allocations and object retention. By examining the allocations instrument, developers can track object creation and identify retained cycles or unneeded references. Combining NS-Zombie with instruments allows for a comprehensive approach to debugging memory-related issues. Automatic reference counting arc simplifies memory management by automatically inserting retain, release, and auto-release calls. Understanding arc rules is essential for writing clean, efficient code. Developers can customize arc behavior using attributes like weak, strong, or unsafune retained to control reference types. Migrating legacy code to arc involves using Xcode's migration tool, which identifies manual memory management calls and replaces them with ARC-compatible syntax. However, this process requires careful review to ensure that all retain and release calls are removed and that reference types are correctly annotated. Recapping advanced memory management concepts, developers must prioritize efficiency at every stage of app design. Techniques like weak references, auto-release pools, and retain cycle detection are indispensable for maintaining performance. Continuous testing with tools like instruments ensures that memory usage remains optimal, even as the app evolves. By integrating these practices into the development workflow, teams can create robust, scalable applications that meet user expectations and adhere to industry standards. Regularly revisiting memory strategies and staying updated with new tools and methodologies will further enhance the quality of Objective-C projects. Today, we will explore how to build a practical Objective-C application that mirrors real-world scenarios. Understanding real-world applications is essential because it bridges theoretical knowledge with tangible outcomes. By focusing on practical examples, you will gain deeper insights into how concepts like object-oriented programming and memory management apply in actual development. Our session today will cover 3 key areas: designing the app structure, implementing its core functionalities, and thoroughly testing the final product to ensure reliability and user satisfaction. Before diving into coding, we must clearly define the app's purpose and identify its target audience. For instance, if the app is for fitness tracking, the audience might be health-conscious individuals. Next, we will outline core features such as user registration, data tracking, and progress visualization. These features will be translated into user stories, which help us understand how users will interact with the app. Finally, we will create a project roadmap that breaks down tasks into manageable phases, ensuring we meet deadlines and stay organized throughout the development lifecycle. A well-structured app relies on the model view controller pattern, which separates data handling, user interface, and control logic. This separation ensures that each component remains independent, making the app easier to maintain and scale. For example, the model manages data, the view handles visual elements, and the controller acts as the intermediary. We will also discuss designing reusable components, such as custom views or utility classes, which can be repurposed across different parts of the app or future projects. This approach saves time and promotes consistency. User interface development in Objective-C primarily involves UI-Kit, a framework that provides pre-built components for creating interactive screens. We will start by designing views and controllers that respond to user actions, such as button taps or gestures. Storyboards and nib files allow us to visually lay out the UI, making it easier to manage complex interfaces. Additionally, we will learn how to handle dynamic updates, such as changing text based on user input or fetching new data from a server, ensuring the app remains responsive and engaging. Data management is critical for any app, and we will explore several strategies. Core data offers a robust solution for local storage, allowing us to store and retrieve data efficiently. For simpler needs, file-based persistence can be used, such as saving user preferences in a property list. If required, we will also discuss integrating SQLite databases or third-party libraries like FMDB for more complex data handling. Each approach has its advantages, and we will evaluate which is best suited for different scenarios. Networking enables apps to communicate with external servers, and we will focus on fetching data from REST-TFL APIs using nSerl session. This involves sending requests, handling responses, and parsing the data into a usable format. we will demonstrate how to parse JSON and XML responses using Objective-C's built-in tools. Asynchronous operations are vital for maintaining a smooth user experience. So we will cover techniques like completion blocks and delegation. Finally, we will address error handling to ensure the app gracefully manages network failures or invalid responses. Testing and debugging are essential to ensure the app functions as intended. We will use the XC test framework to write unit tests that verify individual components, such as data models or utility functions. Xcode provides powerful debugging tools, including breakpoints and the console, to trace issues step by step. We will also discuss strategies for testing edge cases and ensuring the app performs efficiently under various conditions. By prioritizing thorough testing, we can deliver a stable and reliable application. Preparing an app for deployment involves several steps, starting with gathering metadata like the app description, keywords, and screenshots. We will configure provisioning profiles and certificates to ensure the app can be installed on devices and distributed through the App Store. Finally, we will walk through the submission process, including uploading the app to App Store Connect and addressing any review guidelines. Post-release, we will touch on updating the app with new features or bug fixes to keep it relevant and functional. In summary, developing a real-world Objective-C app requires careful planning, thoughtful design, and rigorous testing. From defining the app's purpose to deploying it on the App Store, each step plays a crucial role in the final outcome. Remember to prioritize user-centric design and maintainability throughout the process. As you continue your journey, apply these concepts to personal projects to reinforce your skills and build confidence in real-world development scenarios. In this session, we will explore advanced UI kit components in Objective-C, delving into techniques that elevate your app's user interface beyond standard controls. Customization allows you to tailor components to specific design needs, whether it's modifying the appearance of a picker view or creating unique animations. Layout strategies ensure your UI adapts seamlessly to different screen sizes and orientations, while interaction techniques enhance user engagement through responsive and intuitive gestures. These elements collectively empower developers to build sophisticated, user-friendly applications, creating reusable components through UI view subclassing is a powerful approach to streamline your code base. By overriding the drawrect method, you can generate custom graphics directly within a view, such as drawing shapes or custom backgrounds. Touch event handling, including methods like touches began and touches moved, enables interactive elements, allowing users to manipulate your views dynamically. This technique is essential for building custom controls that respond precisely to user input. Advanced controls like UI Picker View offer a flexible way to let users select data from a scrollable list, while UI Action Sheet and UI Alert Controller provide modern interfaces for presenting actions or alerts. The delegate pattern is key to making these controls dynamic, as it allows you to respond to user interactions and update the UI accordingly. By implementing delegate methods, you can tailor the behavior of these controls to fit specific application workflows, ensuring a more personalized user experience. Auto layout and constraints form the backbone of responsive design in iOS. Using NS layout constraints, you can define relationships between UI elements to ensure they adapt to varying screen sizes. Visual format language provides a concise way to express these constraints, which can be combined with code for greater flexibility. Debugging layout issues is simplified with Xcode's View Debugger, which visually highlights constraints and identifies conflicts, helping you resolve layout problems efficiently. Customizing UI Collection View allows for highly tailored layouts beyond the default flow layout. By subclassing UI Collection View Flow Layout, you can adjust spacing, item sizes, and even create staggered or custom grid systems. Section headers and footers add context to different data groups, enhancing usability. With iOS 11 and later, drag and drop interactions enable users to rearrange items intuitively, making your app more interactive and adaptable to user workflows. Core animation brings life to your app through smooth transitions and dynamic effects. CA Basic Animation allows you to animate properties like position or opacity, creating subtle or dramatic visual changes. CA Transition provides page-based animations, such as sliding or fading transitions between views. UI View Property Animator offers a more interactive approach, letting you animate property changes with precise control over timing and user interaction. These tools transform static interfaces into engaging experiences. Custom gesture recognizers enable unique touch interactions that go beyond standard gestures. By subclassing UI gesture recognizer, you can detect complex patterns, such as a specific swipe or a custom shape. Combining multiple gestures, like a tap and a swipe, allows for layered interactions, enhancing user control. Implementing these recognizers in custom views ensures that your app responds to user input in ways that align with your design vision. Creating a more intuitive experience. Optimizing performance is critical for a smooth user experience. Minimizing layout passes by debugging constraints ensures your UI renders efficiently. Reusing cells in UI collection view and UI table view with decureusable cell reduces memory usage and improves scrolling performance. For image loading, libraries like SD Web Image handle asynchronous downloads and caching, preventing delays and ensuring images appear quickly without blocking the main thread. In this case study, we will build a custom dashboard that integrates UI Picker View for data selection, UI Collection View for displaying dynamic content, and animations to enhance transitions. Real-time data updates require efficient data handling and UI refresh mechanisms. Testing edge cases, such as empty data or unexpected inputs, ensures robustness. Accessibility compliance involves making sure all elements are navigable and readable by assistive technologies. Ensuring your app is inclusive for all users. Mastering advanced UI kit components allows you to create complex, high-quality applications. Prioritizing modularity and reusability in your UI design ensures maintainable and scalable code. Continuous testing and optimization are essential to address performance bottlenecks and usability issues. By following best practices, you can deliver apps that are not only functional, but also visually appealing and responsive to user needs. App deployment and distribution in the context of iOS development refers to the process of making an application available to users through various channels. Deployment involves preparing the app for release, ensuring it runs smoothly on target devices, while distribution focuses on delivering the app to end users either through the App Store, enterprise channels, or other methods. Proper deployment is critical because it ensures that users can access the app without technical barriers. enhancing user experience and satisfaction. This session will cover essential topics such as understanding Xcode tools, the steps involved in submitting an app to the App Store, and the different methods for distributing an app to users. By the end of this training, you will have a clear roadmap for deploying and distributing Objective-C applications effectively. Before an app can be deployed, it is essential to clean up the codebase by removing debug logs, which are useful during development but irrelevant in production. Optimizing performance ensures the app runs efficiently, reducing battery consumption and improving user retention. All resources, including images, assets, and localized files, must be properly configured to avoid missing elements or incorrect display on different devices. Validating app functionality on target devices and simulators is crucial to identify and resolve issues early. This step ensures that the app behaves as expected across various iOS versions and hardware configurations, minimizing the risk of post-release problems. Configuring Xcode for deployment begins with setting up build configurations. Debug configurations are used during development for testing and troubleshooting, while release configurations are optimized for production, ensuring the app is efficient and secure. Target settings require attention to the deployment target, which specifies the minimum iOS version the app supports. Signing and entitlements are vital for security and permissions, ensuring the app can access required features like the camera or location services. Enabling capabilities such as push notifications or iCloud integration involves additional steps in Xcode, where developers must configure the appropriate settings to activate these features. Apple developer certificates play a fundamental role in app deployment by verifying the identity of the developer. These certificates are used to sign the app, ensuring it is trusted by iOS devices. Provisioning profiles act as a bridge between the certificate and the device, specifying which apps can run on specific devices. There are two main types of provisioning profiles: development profiles for testing on registered devices, and distribution profiles for releasing the app to users. Creating and managing these profiles in the Apple Developer Portal involves generating a certificate, associating it with a provisioning profile, and downloading it to Xcode. Proper management of these elements is essential to avoid deployment errors. Registering an app in App Store Connect is the first step in the App Store submission process. This platform allows developers to manage app metadata, pricing, and availability. Preparing metadata includes crafting a compelling app description, selecting relevant keywords, and uploading high-quality screenshots that showcase the app's features. Submitting the app for review can be done directly from Xcode or through the App Store Connect interface. The review process involves Apple's team checking for compliance with guidelines, technical issues, and overall quality. Once approved, the app becomes available to users on the App Store. Testing an app before distribution is a critical phase to ensure reliability and user satisfaction. Beta testing using Test Flight allows developers to gather feedback from a select group of users, identifying potential issues in real-world scenarios. Monitoring crash reports through tools like Crashlytics or Xcode's built-in analytics helps pinpoint and fix bugs that could lead to app crashes. Validating compliance with App Store guidelines is equally important, as violations such as poor user experience or unapproved data collection can result in rejection. Thorough testing reduces the likelihood of post-launch problems and increases the chances of a successful release. Distribution methods for iOS apps vary based on the intended audience. App Store distribution is the primary method for reaching a broad audience, offering public and private options for app visibility. Enterprise distribution is tailored for internal use within organizations, allowing apps to be deployed without going through the App Store. Ad hoc distribution enables testing on specific devices without requiring users to install the app through the App Store. Each method has unique requirements and workflows, and choosing the right one depends on the app's purpose and target users. Common issues during deployment often stem from provisioning profile errors, which can occur due to incorrect settings or expired profiles. Resolving these requires checking the profile's validity and ensuring it matches the app's bundle identifier. Certificate expiration is another frequent problem, necessitating the renewal of developer certificates through the Apple Developer Portal. App rejections may arise from violations of App Store guidelines, such as poor UI/UX design or unexplained crashes. Addressing these issues involves reviewing Apple's guidelines, fixing code bugs, and resubmitting the app for approval. Proactive troubleshooting can save time and avoid delays in distribution. Deploying and distributing an Objective-C app involves several key steps, from preparing the app for release to navigating the App Store submission process. Testing and compliance are non-negotiable aspects of this journey, ensuring the app meets both technical and user expectations. As you progress through this training, remember to practice these concepts in real-world scenarios. By applying what you've learned, you will gain confidence in handling deployment challenges and delivering high-quality applications to users. The final project is the ultimate opportunity for students to apply all the Objective-C concepts they have learned throughout this course. This project requires the development of a fully functional iOS application that meets specific requirements designed to test comprehensive understanding. The focus will be on object-oriented design, ensuring that code is structured with clear classes and relationships. Memory management will be critical, as students must demonstrate mastery of automatic reference counting and avoid common pitfalls like retained cycles. Additionally, the integration of UI kit components will be essential to build a responsive and user-friendly interface. The app must include interactive elements that allow users to engage with the application, implement data persistence to store and retrieve information, and handle errors gracefully to ensure a robust user experience. To succeed in this project, students must revisit and solidify their understanding of Objective-C syntax fundamentals. This includes creating classes, defining methods, managing properties, and utilizing protocols to enforce interfaces. Object-oriented programming principles such as inheritance, polymorphism, and encapsulation will be central to designing efficient and reusable code. Inheritance allows for the creation of hierarchical relationships between classes, while polymorphism enables flexibility in method implementation. Encapsulation ensures that data is protected and accessed through well-defined methods. Memory management in Objective-C relies heavily on automatic reference counting, which automates the process of tracking and releasing memory. However, students must be vigilant about retained cycles, which can occur when objects hold strong references to each other, leading to memory leaks. Finally, the UI kit framework will be used to construct the user interface with a focus on views, view controllers, and other components that bring the app to life. As students work on their projects, they may encounter several common challenges. Debugging memory leaks and retained cycles can be particularly tricky, requiring a deep understanding of how objects are retained and released. Students should use tools like the Xcode instruments to identify and resolve these issues. Managing asynchronous tasks, such as network requests or background processing, will also be a key challenge. Techniques like Grand Central Dispatch or NS Operation can help coordinate these tasks efficiently. Designing a scalable and maintainable code architecture is another critical aspect, as students must avoid tight coupling and ensure that their code can evolve with future requirements. Integrating third-party libraries and APIs will add another layer of complexity, requiring students to understand how to handle dependencies, manage versioning, and troubleshoot compatibility issues. The final project submission requires a working iOS app along with its source code and documentation. The documentation should explain the app's functionality, design decisions, and any challenges overcome during development. Students will present their projects in a 10-minute demo session where they will demonstrate the app's features and explain their implementation. The grading criteria will focus on 3 key areas: functionality, ensuring the app works as intended; code quality, emphasizing clean, well-documented, and efficient code; and creativity, rewarding innovative solutions and unique features. The deadline for submission is insert date, and students must upload their work via platform name. It is essential to plan ahead, test thoroughly, and adhere to the guidelines to meet the expectations of this final assessment. This course has equipped students with core Objective-C skills, from syntax fundamentals to advanced object-oriented design. The emphasis on real-world application ensures that students can translate theoretical knowledge into practical solutions for iOS development. As they move forward, I encourage students to continue exploring advanced topics in iOS development, such as Swift interoperability, advanced UI kit features, or even cross-platform frameworks. Feedback from students is invaluable for improving future iterations of this course, so I welcome any suggestions or insights they may have. By building a strong foundation in Objective-C and fostering a mindset of continuous learning, students will be well prepared to tackle more complex challenges in the ever-evolving world of mobile development. And just like that, our dreamy coding adventure has come to an end. I hope the gentle ebb and flow of the tutorial, combined with the tranquil melodies, have left you feeling both informed and at ease. Whether you managed to catch every line of code or drifted off into a peaceful slumber, remember that the world of Objective-C will always be here waiting for you. Keep your code clean, your mind open, and your spirit relaxed. Don't forget to subscribe to Code Snooze so you never miss out on another soothing coding journey. Hit that like button if this video brought you a moment of calm and learning, and share it with fellow coders or anyone in need of a serene study session. Thank you for joining me in this cozy corner of the internet. Until next time, may your code run smoothly and your dreams be filled with brilliant algorithms. Sweet dreams, sleepy coders.